I had little badges made with the QuTiP logo, and I'm going to give each of you one if you want one. So maybe I should start by, I mean, you can just say hello. We're quite a small group, so I'm hoping we can kind of keep this informal. Feel free to stop me kind of whenever and ask questions. And I'm hoping that, when interesting things come up, we can just have a conversation about them. In terms of sort of how the tutorial is going to work, we have a kind of, I guess, sort of kind of exercise, which is going to be the kind of focus of what we're doing, which is to try and kind of really simulate, kind of really almost at kind of a reasonably low physics level, a neutral atom quantum computer, which is actually not, I mean, it's not a huge amount of code if you're using QuTiP, but there is a lot to understand, and I think it's really important to kind of understand what we're doing as we go along, because otherwise it'll be really hard to use it later, and presumably the kind of point of the tutorial is that you want to be able to kind of do things. So that's kind of how things are going to work. My name is Simon. I'm currently lucky enough to be employed to work on QuTiP full-time by a research institute in Japan called RIKEN. I'm not currently based in Japan because of COVID, so Japan just closed its borders, and I got hired in the middle of all of this. So I had a fun time. Like, I rented out my flat, and then was told, no, you can't come to Japan, and sold my car. And anyway, it was a huge mess. But it was also, I think, it was also kind of lucky. And so now I'm working for them remotely. So I'm based in the Netherlands, where me and my wife live. She also does maths and physics, but originally from South Africa. In fact, was kind of in South Africa, well, I mean, except for some short trips, kind of my whole life up until June last year. Anyways, that is me. Before I get started, I'd also like to maybe learn a little about all of you, and particularly the stuff that is, I guess, important to today. So like how much people know, like what things should we just skip over and be like, okay, we all know this, and what things, where should we kind of spend our time? Also, I'm intending for us to kind of take a short break, sort of every hour, or I guess a slightly longer break in the middle, when hopefully there'll be coffee and snacks and things. But please let me know if I forget. I know, maybe we'll just start kind of on the right. You can just say like one or two sentences about your background and yes, you.
Okay. My name is Vari. I'm from Capital One. I work on data engineering part of MLD.
And do you have something specific that you kind of wanted to get out of this tutorial? Like, just curious, or?
I'm very curious to know quantum technologies and how it will empower, machine learning decisioning.
Okay.
Yeah.
Cool.
And to know the trends on it. Yeah.
I'm Luke. I'm a grad student at UAB in computational solid-state physics, and I just thought this would be a great teaching tool for new students.
Well, awesome. I've actually had quite a bit of luck using QuTiP for undergrads, and maybe we can chat a bit more later. But I think there's some really nice things about these kind of simulated quantum systems from an educational perspective. Obviously, the problem with like a real quantum system, and you kind of see this if you're sort of working with students, is it's either all like equations, which is one part, or then you take them into the lab, and suddenly they're spending like 2 hours trying to properly align like the laser and the polarizer, and understanding what is going on has gotten lost in this sort of pile of lab equipment that they're trying to learn and manage. So so simulated systems have this sort of potential to like look inside and kind of debug either the code or your understanding. Awesome. So I guess you know a lot of physics. Okay. I mean, there's kind of an infinite amount to know at this point, or at least effectively infinite compared to like one person's lifetime in brain. Yep.
So I'm Braga. I'm a PhD student in Melbourne in Australia. I'm really just here out of curiosity. I don't know much about the quantum world.
Mm-hmm.
I mean, I have like a super basic
Yeah.
understanding, but not, you know, as it like really pertains to quantum computing. But yeah, I just thought it would be super interesting.
Well, so I find that people by super basic, people mean everything from like, I don't know, like I'm Richard Feynman to like.
I'm not one of those. Yeah, so like my background's in computer science, so
Okay.
I know that side of things really
Okay.
well, but physics is only like, you know.
Okay, and kind of, have you done like a first year physics course at university or?
I have, but
Okay.
it was a long time ago.
Okay, cool. I mean, that's good.
I'm James,
Yeah.
also from Melbourne. I teach some computer science. I do a little bit of work on Pi as well here. And again, I have, my question would be like, what is a qubit type thing? That's my level of understanding.
Okay.
So if I'm slowing down, I'm just here out of curiosity, so don't worry too much about that. Yeah.
Well, I mean, I'm going to do my best to keep everyone with us and on the same page. I would rather actually spend more time kind of getting everyone to understand the basics well, because that will at least give you a solid foundation for doing more. Good. Yes.
All right. So I'm Brian. I'm from the Naval Nuclear Lab in upstate New York, and I've got an experimental physics background, so this is very interesting to me, just kind of seeing like how it all fits together in kind of the computer science informational type space.
Good. Yeah, I mean, QuTiP is used, well, actually, QuTiP tends not to be used, well, there are some experimentalists who are very comfortable with like tools like QuTiP and who happily use it themselves. But I think what I found more often is that the experimentalists will come to other people who are sort of theorists who use QuTiP and be like, hey, I'm working with this thing in the lab, what can you tell me? So, good. Okay, maybe since people are okay, yeah. So I'm going to do some kind of high-level stuff first, and oh wait, there's actually one more thing. I wanted to ask some specifics about kind of what people know. So I guess hands up if you feel that you're comfortable with, say, just kind of like I guess basic linear algebra. So like matrix multiplication, or happy, okay. So, I don't know, like eigenvectors, eigenvalues, okay, a little bit shaky. That's good. Yeah, I mean, we actually need very little of linear algebra beyond, beyond matrix multiplication. There's some things, I guess, quantum mechanics uses sort of linear algebra in some slightly strange ways that are not typically taught in the kind of, I guess, basic physics course. So you have these kind of outer products, so which is just kind of matrix multiplication, but it's the kind of matrix multiplication which sort of you just never do in like a first year linear algebra, or at least I didn't. Yeah, so shout if there's any kind of linear algebra stuff which is odd. Complex numbers. How are people feeling? Okay, good. Everyone seems good on complex numbers. That's useful because quantum mechanics is filled with complex numbers. Cool. Awesome. I want to say one more thing before we get started, which is actually just to, I guess, sort of, obviously, like this tutorial doesn't exist in a vacuum. There is kind of obviously QuTiP. QuTiP itself is primarily funded by RIKEN in Japan, who I work for. Yes, RIKEN actually were working on Japan's nuclear weapons program at the end of World War II. But then, and obviously when the World War II ended, that was hurriedly shut down. But the Japanese kind of just sort of renamed it and got rid of the nuclear weapons program, and then a few decades later renamed it back to RIKEN, and it continued on its way. But it became a lot more diverse. It was initially very physics focused, but now it covers, I guess, kind of sort of fundamental physics, kind of material science, biology, quite a lot of neuroscience, so quite a very wide range of things. Then sort of on the open source side, so QuTiP was started about 10 years ago by 2 PhD students who were working at Ricken, and well, they kind of started during their PhDs, and then it really got going during their postdocs at Ricken, and so yeah, those are Paul Nation and Robert Johansson. Paul Nation is actually now with the various QuTiP teams at IBM. And in fact, if you look at QuTiP, you will see lots of similarities to bunches of QuTiP code because Paul wrote both of them. And obviously he was like, I don't want to really start this from scratch. I'm just going to write a slightly better version. And now QuTiP is run actually by a very sort of widely dispersed group of people, mostly within Europe. But there's a kind of core admin team who meets once a month. Not everyone is always equally active. So Nathan Shamana is heavily involved in the Unitary Fund, which is this, I guess it's a small, I guess, sort of investing and sort of donation fund that funds specifically open source quantum projects. And they have these grants that they issue regularly, and they're really like a 5-minute grant application. So it's just like a Google form that you just type in some stuff. So if you want to build something like on top of QuTiP, and it would be useful to have like a little bit of funding for it, you can just look up Unitary Fund, fill in their form, and they are kind of, because they do quite small grants, so like $1,000 to $4,000 typically. But they also kind of give them quite quickly, so you can kind of probably get a grant in like a month. Anyway, if you want to have money to do stuff with QuTiP, like, I don't know, build like a tutorial or like a little course, I don't know what people want to do, but anyway, it is there. And then there's one other person other than me who works relatively full-time, and he will actually be here at the main conference on Wednesday. His name is Eric Gagier, and he's in Sherbrooke in Canada, and he works for a big HPC group there. Okay. Cool. Okay, so maybe getting into kind of what QuTiP does a little bit. So if you've done a kind of basics physics course, you're probably mostly focused on, I guess, what are called quantum systems, but which are people usually mean kind of very isolated systems. And the initial system that people looked at was really the atom. And of course, there are different kinds of atoms, different elements, different isotopes within elements. But a lot of quantum mechanics just came out of examining these atoms, and that's going to be, well, I mean, atoms are also going to be important to this tutorial because we're going to look specifically at neutral atoms, and we look at kind of the details of their physics a bit later. This world of atoms turned out to be quite strange. So I mean, it's a very, I mean, atoms are very small. So just the radius of the atom. So that's kind of roughly sort of, if you were to imagine sort of where the electrons are. Of course, now we know from quantum mechanics that the electrons are not sort of anywhere specifically exactly. They're sort of kind of like the state is a more distributed state. Then that's about like 0.1 nanometer, so 10 to the minus 10 meters. And then the nucleus inside that is more in the range of kind of 1 femtometer, so it's like 10 to the minus 15 meters. So the distance, well, the size of the nucleus compared to, it's like only like 1/10,000th of the distance from the nucleus to kind of where the sort of electrons are, very roughly speaking. I think maybe something that I want to say just about kind of, I guess, the development of quantum mechanics is that I mean, I think it's became over the last 100 years just sort of this kind of adage that is sort of trotted out that quantum mechanics is kind of super weird, not understandable. But I don't think the people developing quantum mechanics kind of thought that initially. I mean, if you look at quantum mechanics, a lot of the tools used, like Hamiltonian mechanics and Lagrangian mechanics, these were all formalisms from classical mechanics. That people like Schrödinger and kind of Dirac were kind of very familiar with. And if you kind of read their papers, they are clearly masters of these classical mechanics, because obviously that's what physics was kind of prior to this. And a lot of the stuff that we consider strange and sort of weird in quantum mechanics, I mean, even stuff like Heisenberg's uncertainty principle, and the fact that kind of our sort of measurements that we do, or like our operators on this like space of wave functions, that actually all crops up in kind of classical mechanics if you're working with continuous systems. So I think, well, one of the things, there are definitely some very kind of strange things lurking in quantum mechanics, but there's also a lot that we can kind of understand, I guess, using our kind of classical intuition. Okay, so QuTiP models kind of open quantum systems, and I'm hoping that we'll kind of properly maybe get to some like real open quantum system stuff at the end. But what is the difference between an open quantum system and a normal quantum system? So a normal quantum system, which I guess to distinguish we can call a closed quantum system, is kind of completely isolated. So we know exactly its state. We know that it evolves according to an equation called the Schrödinger equation, and that just evolves completely sort of deterministically using this kind of linear equation in time. And at some point later time, we have this kind of exact thing, and we kind of, well, maybe we'll look at the Schrödinger equation a bit later, but it's even not that hard to solve. We know that kind of we look for the kind of eigenstates of the kind of evolution operator, and then we decompose our initial condition into these eigenstates, and then we know how those eigenstates evolve, and because it's linear, we know how sort of the composition of them evolves. And so then we've kind of solved everything, modular having to do a bunch of like kind of painful mathematics. But there is one thing which kind of happens sort of completely outside this formalism, which was, the problem was always sort of how to connect this completely isolated system to the lab, because obviously to get results out, there needs to be some interaction between the lab and the system being studied. And in atomic physics, it's kind of simple, the way you interact with, I mean, it's, okay, well, simple is maybe the wrong word, but at least it's kind of conceptually simple. The way that you interact with an atom is with light, because it's mostly sort of, well, at least, yeah, in atomic physics, mostly interact with some particles that are coming in and out. And given the sort of scale of kind of the atom, the particles are really traveling a very long way. So, I mean, it's kind of traveling, like a photon is emitted by an electron, which is, say, kind of from this little kind of atom, which is, say, 0.1 nanometers across. So it's like, and then it travels, say, like 1 meter to some detector, probably, but on the order of 1 meter. So it really travels like 10 to the 10 times more than the size of the system that was being kind of studied. So it's really made it a kind of very long way away. Yeah, and then kind of what we found was that there was a strange rule for determining kind of when photons were emitted and what we detected. And I think we can sort of summarize what happened there was like, well, we have a rule which works, but we don't really understand why in any detail. And so this kind of question of how these tiny quantum systems couple to kind of larger environments and what really happens there remains, I mean, to this day, I think still a little bit of a mystery. But in the intervening period, we did actually, humanity physicists did make some progress on this. Like what happens if you take a small system and kind of connect it to a larger system. So people started kind of asking, I guess, good physics questions. So kind of, what if we don't try and connect it to a big system? What if we initially just connect our tiny system to another tiny system, and then, say, separate them and kind of ask about how those interactions work? So this study of kind of quantum systems that are connected to other quantum systems is called open quantum systems. So maybe I'll just draw a drawing here. So you've got typically that's visible to everyone. Oh, okay, so you have some tiny system, and then I can just draw around it. We're going to have a bigger environment, and the kind of starting point of open quantum systems is that you make a joint system, which is both the kind of system and the environment. But and now conceptually, this is all completely fine. You can do this within kind of ordinary kind of quantum mechanics. You have some very large kind of closed quantum system now, but this system is too huge and unknown to solve. So what you have to do is make some sort of approximation for the environment and how it interacts. So I didn't use this comma to label what the interaction is. And then what you do is you take the approximations and you try and use those approximations to simplify kind of the dynamics and work out how things are going to evolve. So maybe what are some of the simplifications that people use? One thing you can do is you can assume that that the system has kind of like no, or it means actually look up my list. Well, I guess one of the simplest assumptions is that the kind of bath is kind of completely dissipative, and what this means is that kind of, say, like a photon can sort of leave the system and enter the environment, but nothing can come back. So dissipative is just a sort of one-way flow of kind of, well, you can think of it sort of as really energy, but just sort of the system kind of affects the environment, can sort of lose stuff to the environment, but nothing ever comes back. Another assumption that you can make is, and this dissipative model is kind of one of the easiest to deal with. So another assumption that you can make is that the bath has no memory of previous interactions with the system. So that means that kind of if say, I don't know, a photon is emitted by the atom, or if a photon is absorbed by the atom, the environment always just kind of stays the same. It's kind of from time to time, it's always kind of, it maybe has some sort of well, yeah, from time to time it's just kind of always the same and nothing is kind of happening there. And then things got kind of more complicated. So you can then do things where you assume that the system does have memory, but that the free bath is Gaussian. So it's kind of a thermal system, but it does have internal state. And say photons can kind of enter the thermal system and kind of sort of fill up kind of energy levels and things. Yes?
So when you say that is that E, that
oh, yes.
environment?
Sorry, thank you.
I've seen that phrase used a lot in the literature, and I kind of have like a hard time understanding what they're meaning. So that means your external environment that's influencing your system.
Yes, yeah. So sorry, I'm committing the same kind of problem that you see in the literature, which is that people tend to use environment and bath somewhat interchangeably. I guess the word bath comes directly from thermal bath, and kind of most of the kind of situations that you kind of imagine, there is a kind of a thermal character to the bath.
Can I just
Yep.
add? So those simplifications of the system, are those written in order of like increasing complexity? So like a dissipative system is simpler than a Markovian is simpler than a Gaussian, or they're just different ways?
So there is a sort of I would say that the kind of Markovian case contains the dissipative case.
Mm-hmm.
The Gaussian case, I would say, is more complicated than Markovian, but they're sort of different assumptions.
Mm-hmm.
Not I wouldn't say completely that one contains the other.
Mm-hmm.
So kind of open quantum systems started out kind of again as sort of really people were like, we really want to understand some like fundamental problems better. And then kind of alongside, I guess, the sort of theoretical development and kind of going along with it was a lot of experimental work that was quietly happening in the background. And people started actually kind of really making these kind of dissipative systems. So people would do stuff like they would make kind of a cavity with two mirrors, and they would sort of shine kind of a bit of light into the cavity, and the light would bounce backwards and forwards many times, and it would enter some sort of kind of stable kind of sort of thermal state. And then you would put like an atom in the center of the cavity, and you'd watch how those things interact. And so the atom could kind of lose a photon, but then the photon wouldn't just disappear off into the middle of nowhere. It would sort of bounce backwards and forwards with the other photons between this mirror, and you can get kind of all sorts of kind of exciting states. People, I guess, started making sort of things like Josephine junctions, which are these kind of superconducting junctions where, because sort of you can get sort of superpositions of different states of current flow. And these are, from a quantum mechanical perspective, almost basically macroscopic like objects. I mean, there's current flow that is making your kind of quantum system, and what isolates it is the fact that the current is not really coupled to anything. It's just kind of flowing frictionlessly by itself. And then obviously with the engineering of kind of these things like these Josephine junctions for all sorts of amazing applications, like there's a really simple circuit you can make which can sort of measure individual quanta of magnetic flux. And then once you can measure quanta of magnetic flux, you can convert other things you want to measure into sort of changes in the magnetic flux. And then you can measure all sorts of things very accurately, and these are called squids. And people are very excited. But then, of course, in reality, nothing is completely sort of frictionless. There's all sorts of little interactions. People want to understand all of the details, and so kind of open quantum systems came in again. Cool. And so QuTiP is very much designed to, I guess, support kind of people who are doing research in open quantum systems. To do research in open quantum systems, you kind of have to also do research in closed quantum systems. I mean, you have to have all of quantum mechanics around. And so QuTiP supports closed quantum systems, but then kind of what makes it maybe a bit special from a sort of academic kind of researcher point of view is that it has kind of a lot of stuff to support these kind of open quantum systems and for working with them. So you can imagine that sort of as you make kind of different approximations here, the equations which govern your dynamics are different. You need different kinds of solvers. You need, actually, really the solvers in some ways are the easy part. It's all actually constructing the system to solve the right way is often the hard part. And I think maybe something else which distinguishes QuTiP a bit, because there are a growing number of very specialized tools, is that QuTiP has just actually really nice ways of describing really basic things like quantum states and Hamiltonians, and combining them and visualizing them. And there's all kinds of common things you want to do, like find eigenvalues, find eigenvectors, so kind of all of these things sort of exist within QuTiP, and I think that's kind of part of what makes it a nice, I guess, like a nice teaching tool, but also makes it very convenient at the research level. It's quite nice that, and we'll actually maybe do this a bit later, can actually take like equations from papers and sort of type them into QuTiP if you know kind of roughly how to translate them, and it's probably no different to some extent to having to type those equations in later. I mean, it's a slightly different sort of language and formalism, but it's kind of the same level of translation, and that's quite nice. And also kind of avoids lots of mistakes. Like the more translating you have to do, like I make enough mistakes already without things being complicated. I think the other thing which is great about QuTiP is it's very general purpose. So it obviously comes with some downsides. So if you have a very specialist task, I would look for a specialist tool before kind of writing stuff. But if you're kind of generally exploring, it's kind of really nice to have a general tool as well. Good. Good. Okay, so much for kind of introductions. Maybe any questions or more things we want to talk about right this second? Are we good to go? Good.
Is there a website for this? Will you follow up?
I'm going to put these kind of all online as soon as I've cleaned them up a little bit. But yes, but you don't feel the need to copy anything down. I will make them available. Good. Yes.
So when you talk about open quantum systems, it's strictly a system interacting with its environment. It's not two systems interacting together? Or is that a nonsensical question?
It's not really a nonsensical question. So you could, for example, you would use, it's really about, I guess, the size of one of the systems and whether the entire system is sort of, whether this complete system, the complete picture of both the system plus environment, like if you can just solve that by itself, then that's the best thing to do. You just use ordinary quantum mechanics, you solve this system, and then you can extract whatever information you want from the result. And so that's like first prize, if you can get it. So what makes a system open is, I guess, so people often do study kind of small systems coupled to each other. Maybe let's make this super concrete. So let's say you have like two, say, atoms here coupled in some way, maybe by the spin of the electrons or something. And I don't know, here you have kind of a heat bar, so really like a little source of photons. And here you have another heat bar. I'm sort of intentionally drawn this one a bit lower to indicate that this is like slightly cooler. Then this is like kind of like a heat engine, quantum heat engine thing that people study. And you look at kind of how the heat flows through the system. So I'm not sure if this quite covers the case you're looking at, but if and the models for these environments are quite simple. I mean, if they're again some sort of probably some sort of like optical cavity or something. So I'm not sure if that counts. But the reasons for using open quantum system techniques is that the environments are very big. Or you can't know everything about the environment is also kind of another common case. So you know sort of statistical properties about the environment, but there's no way you can kind of know its kind of internal behavior exactly. So if it's really big, or if it's just kind of really noisy, so does that, yes?
So with the three different models you got up there, so dissipative, Markovian, Gaussian, do they differ in the sense that they have different noise models, or is it also in like the way that you actually solve the behavior of them?
It's actually the way that you solve the behavior of them, and I guess these all cover actually a few different specific kind of approximations live within these broader descriptions. So yeah, it's more actually about how, if you put on your like quantum information hat, it's about how information moves between the system and the environment. Or if you put on your physics hat, it's how energy moves between the system and the environment. yeah, so for example, particularly this these Gaussian ones, I would say there's, I don't know, like, I would say probably like at least 10 major sort of techniques which sort of fall within that, which sort of share some, what this Gaussian approximation really gives you is that when you plug the fact that the sort of environment by itself has this kind of Gaussian distribution of states to start with, when you plug that into like a giant path integral, your correlation functions turn out to only depend on differences in time, and that makes a whole bunch of things simpler. So, yeah. Maybe I'll say there's a lot of stuff that's kind of I haven't mentioned here, and stuff that I also don't kind of quite know. And there's a lot of new stuff happening from the quantum information side. So I guess you can look at like tensor networks and stuff as either as kind of new techniques from quantum information, or as techniques that are kind of new techniques within open quantum systems. Good. Yes. Good. Cool. Okay, so I want us to kind of just do a quick run through of like what really is like this device that we're going to be simulating. What does it do, and what does it physically look like? And one of the things I always struggle with when I'm reading papers is you'll read a paper about some things like spin qubits or like neutral atom devices or photonics, and then there's like 30 references in paragraph 1, which are supposed to kind of, somewhere in those 30 references, a description of what's actually going on, so you can visualize the device that you're working with. Anyway, so I thought it would be nice just to go through and really get like a physical understanding, which will help us later when we're thinking about all of these strange things. Let me just make a big image. Okay, so yeah, so these images were made by a French team just outside Paris. They were all in kind of academia doing these kind of neutral atom devices, which we'll get to more in a second. But then they founded a startup called Pascal.io, and I stumbled across them, and I got some students to do a sort of similar thing to what we're doing in this tutorial now. Anyway, but let's kind of have a look at kind of what's on the screen. So these are pictures of atoms in space, and you can see on the kind of axis here, you can see this is kind of about 100 kind of micrometers, and each of these little points is an atom. You can see from the fact that the points are a little bit blurry, and also from the fact that they're kind of quite big, that these are kind of very blurry pictures of the atoms. And kind of remember that the size of an atom is sort of 10 to the minus 10 meters, and so here this is like 10 to the minus 6. So they're very far apart, and much further apart than you would get in a solid or even a gas. So we can kind of already tell from the pictures that these sort of atoms are very far apart from each other in a vacuum somewhere. But then the question is sort of what is holding them up, and how did they get here? And I don't know, I think it's really kind of just important to take away. It's kind of incredible that we're sort of have arrived in a world where really we can make a picture of the Eiffel Tower by arranging kind of atoms in space kind of however we want. And as you'll see in these devices, we're really able to control kind of really an electron within each atom kind of individually, and move it through kind of quantum states kind of with a lot of precision, which is kind of incredible. I think if you'd gone back to the founders of sort of quantum mechanics and be like, hey, we can put like 100 atoms like anywhere you want and kind of probe them individually, and kind of make them change, see how they interact, they'd be like, okay, let me like have the experimental device. I'm just going to churn out papers. But I think it's kind of just exciting that this is one of probably like 8 different like physical systems which are really getting getting a really solid experimental handle on, and people are already, like all of the people who are doing like building quantum computers, like whenever you speak to one of them, they're all like, okay, like we're done with like sort of 100 qubit devices. What we're planning for now is thousands, and that's kind of the next goal.
So, excuse me, sorry, are
yes.
these like reconstructions or diagrams or like?
Oh no, these are actual photos.
Yeah.
Yeah, so these are actual photos. So I'll show you how the photos were taken in a second.
Yeah.
So I mean they're, yeah, I mean the actual spots obviously they didn't. So there's a lens that takes the light being emitted and kind of spits it out for a CCD camera. Maybe let's. Maybe just say we can also tell from these pictures that kind of these must be neutral atoms, because even if they had like a single charge, the sort of the like electronic repulsion pulling them apart would be huge. Well, initially it would be very huge, and then they would disperse rapidly. Okay. Okay, let's maybe actually have a look at the actual device. So most of these pictures I've borrowed from the Pascal team. So, okay, here on the left, we can see the vacuum system, and that tiny little dot is kind of where the atoms live. And so there's a little, so the atoms are, they're alkali, so the important thing is that they have just a single outer electron, which makes everything like easier to control. And so you can see here this. So I guess the first thing you can see is like the purple, the red, and the green light are all laser light. So I guess we kind of needed quantum mechanics so we can invent the tools which will allow us to investigate quantum mechanics more. We're going to look in more detail on the left. So the red light is the light that is being used to trap the atoms in place. And this little plate here on the right, the SLM, which so the Spatial Light Modulator, a very Star Trek name, like Spatial Light Modulator, but it does exactly what it says on the tin. That it's a kind of bumpy surface. So the laser light bounces off this kind of very carefully made bumpy surface and then interferes with itself. And where you get constructive interference, you get these little traps which hold the atoms in place. And you can make sort of all sorts of like complicated configurations. So that's how you kind of get sort of by changing the bumpiness of the surface. So you've got like a bumpy surface there which you can control. And then you have this next thing, which is the purple light. Okay, so the purple light is so that's like just a sort of single laser, and it's used to move the atoms around between the traps. And we'll actually very shortly watch a very short video of like how they do that. So you use the red light to set up all of these little traps in space. Then you take a tiny bit of kind of gas filled with atoms, and you just let it disperse into the traps. And then, so they kind of, obviously, then the population of atoms in the traps won't be exactly what you want, but then you use the tweezers to move the atoms around. And then the green light you use to photograph the atoms. You shine the light on them and look for their fluorescence. And this dichroic mirror just means a mirror which reflects lights of different colors in different directions. So that's green light is just when the measurement comes out, it gets bounced towards a camera, which is really a CCD camera, kind of like you would get in in our cell phones. And then and if you use the vacuum system, the vacuum system is also kind of very cold inside. So that's actually the laser. I mean, it's very cold partially because you kind of have to be very cold if you're going to have a vacuum, but also it prevents the atoms from kind of bouncing out of the traps. And the traps themselves, actually, by trapping the atoms, confine their momentum. As in the momentum has to be kind of close to zero because they're not leaving the trap, and that also cools them down. Cool. Maybe I'll just say one. So this is this AOD, the acoustic optical deflector. Yes, another Star Trek kind of name, acoustical optical deflector. That really is, you basically put frequencies into it, and it kind of wiggles the mirror according to the kind of the signal generators you put in. So yeah, so this is kind of like a tiny 80s disco. There's laser lights and sound playing and yes. Well, not yet. Also wanted to just maybe look. I just wanted to look at this picture of the experimental apparatus. It's very similar, except that makes a few things clearer. So you can actually see there the structured light modulator. You can actually see really that is actually one of the pattern on the picture is actually one of the patterns they use for creating lattices. And you can see it's got a sort of, it's just colored according to the phase. So obviously the phase for light is determined by how far it travels. So it travels slightly shorter path or slightly longer path. And really you can kind of control this 2D surface. Yeah, and then what you get out is from the in the traps is a Fourier transform of this 2D phase. So you kind of that's kind of how if you have to design a trap, what you have to do. Oops. Okay, let's watch the short video of. Let's make it bigger. Yes. We're going to kind of hop through some of the experimental pictures again, but this is all going to be just in 2D, and the way you do 3D is you have multiple layers of 2D and you fill them one layer at a time. There's also, I guess, one sort of technical detail here is you might sort of initially think okay, we just fill the traps with as many as we just put in slightly more gas than we need, slightly more atoms than we need, and then we fill up the traps as much as we can. But actually what happens, because the traps are so tiny, if two electrons are in the same trap, they kind of collide with each other and then just scatter out of the trap at high speed. So you actually end up underfilling the traps, and then we'll see what happens next. Okay, maybe this point here is which creates this sort of kind of 1 micrometer waste, which the atoms are trapped near. Yeah, just kind of looking at the temperature here, and you can see things. The real signals that come out. So if you kind of get light, you get this sort of bumpy signal, but if you don't, you get this kind of lower weakening signal. So this is kind of real data. Actually just pause here. So these are some pictures of the the shape put onto the modulator and then the array that you get out. And maybe if you're really good at 2D Fourier transforms, you can even somehow see that these are related. Okay, so here the dots are all of the traps that have been created, and these little boxes are where they want the atoms to end up. So this is them actually moving like one atom around at a time. I think they just made, I don't think they actually made, well, maybe they did actually make the words, but. Oops. Yeah, I wanted to say a little bit more about just like trapping one atom, because that was worth 1/2 of the Nobel Prize in 2018. So it was clearly not, it's clearly not a trivial thing to do. But actually, it's kind of a whole topic by itself, just like doing the kind of mathematics of how the traps work. Right. Okay, maybe before we kind of, I guess, move on from the, any questions about just the physical setup at the moment? Anything you want to look at again? Yeah.
How quick did that experiment take? Or how long did it last? It was some microseconds, like thousands?
It was milliseconds was the counter. So I think like tens of milliseconds.
And during that time, it was pushing a tree who was pushing, not a tree, but like, a tree who was pushing around the atoms physically.
Yes.
That why did it move so quick? I mean, it's amazing. It's so cool that it does. But why do you guys think it would move so quick?
Yeah. So bear in mind that the kind of speed is kind of velocity. So that, they're not moving big distances, which is what helps. So they're moving like each of those traps is only like a couple of micrometers apart. So you have to move like 10⁻⁶ meters. yeah, but that was slow. So that was slowed down 1,000 times. So if you can maybe use that to get a sort of visceral feel of how long this takes.
So, because you know how it was moving stuff around to adjacent tracks,
Yeah.
right? So, given any initial, and I'm assuming like a computer solves this, right? Because it's happening in like.
Yes. Yeah.
Right.
Yeah.
So, given any initial configuration of the trapped atoms and the desired pattern, have they optimized for like the minimal number of steps to like rearrange them?
Oh, so it's a little bit tricky because it is a closed loop control thing, as you said. But you don't know exactly which traps are going to be filled initially. So, because you just have a sort of gas of atoms which go into the traps, and then you actually have to take a photograph using the CCD camera that we saw and the green light. And then the computer has to process the image and then find out where the atoms are and then design the moves and then control the little sort of disco light display which moves stuff around, the AOD. So all of that, so finding algorithms to kind of do that quicker is really important. And I think as we'll see, you've got, it's quite common in quantum systems. So as you slowly interact with the environment, which happens kind of to some extent, whether you like it or not, typically you lose some kind of the kind of special behavior that you're trying to keep, because it just kind of gets lost and kind of merged in with the environment via sort of noisy process. So there is a kind of clock that is ticking on all of, this happens in all of the sort of quantum devices at the moment. And neutral atoms are actually fairly good. So the kind of amount of time that they can last if they're just sitting there is on the order of milliseconds, which is quite long compared to probably like 1,000 times longer than like the superconducting qubits, just because they have a much more kind of macroscopic thing that's actually like physically on a piece of silicon and such. But all of those all of those sort of milliseconds count. And if you've got 1,000 and you use like 50 kind of as part of like your setup, it's a problem. Well, not like a huge problem, but it's something that you would like to be better. Cool. So I want to maybe talk about like what does one need to make a quantum computer. And in 2000, a physicist named DiVincenzo came up, who actually was working at IBM, came up with a list of kind of criteria that are called the DiVincenzo criteria. Usually they're listed as 5. There's 2 which are for creating like quantum networks. But anyway, I thought we'd just have a look at like what we've just seen matches up to those criteria. So is there any kind of eraser? Yes. So you need, first of all, you actually need like a scalable physical system. With qubits, and we'll talk in a bit more like what qubits are already. They're just like two-state quantum systems, or like quantum systems with 2 basis states, but we'll look at them a bit more. But in our case, our qubits are just going to be the individual neutral atoms, or actually an electron on the individual neutral atom. But maybe I'll put just like a big tick here for this particular physical device. So it's really, from a point of view of kind of the like physics of the underlying system, it makes kind of great qubits in some sense, because the atoms are very far apart. They're neutral. Like they're not really interacting with anything. They're held in place by the traps, but the traps are not really kind of affecting kind of the state of the system too much. The decoherence times, the amount of times that it retains its state nicely are actually kind of ludicrously long. And as we can see, IBM now are starting to be okay, we'll have, I think, like 100 qubits, like superconducting qubit systems, maybe like next year or something. But the neutral atom people are 100, we can really, 200, we can do those easily. So it's really great on that side. And I guess you can now sort of see a bit of computer science creeping in here. So you've got to have a way to represent your kind of the state of your system. You have to be able to initialize the system. So we've seen, I guess, the kind of moving around of the of the atoms. The one downside of the of the neutral atoms with initializing things is that it's quite difficult to initialize individual atoms. It's sort of with the superconducting qubits, you can really just feed in different signals into different wires, and you can you can initialize different different qubits differently, by feeding them different signals. Here, you kind of just sort of try and move everything drive everything into one particular kind of energy state, and you just sort of bathe the whole sort of 1 micrometer sort of region, so the whole little region with the atoms in, and you kind of drive them all into one starting state. So you kind of have one global starting state, which is not the end of the world by any means, but it means that if you want to get a more complicated starting state, then you have to do some other transformations of your system after initializing it. I'd call this one a semi-tick for neutral atoms. Maybe could be better. And people are sort of looking at how to do this. I think one of the things that you can kind of, if you had really an optical tweezer per atom, you can do more, but yeah. Okay, so the next thing that one needs is long decoherence times. Decoherence is the kind of technical term for just sort of losing your quantumness to the environment. And it was probably, say the decoherence sort of program was probably one of the first really big successes of open quantum systems, was just kind of, I guess, showing that happens quite generically. Maybe we'll put that sort of a double tick there. So it's good. Okay, so the next one on the list is to have a universal set of gates. There's a set of operations. You can, many of them are analogous to existing kind of classical logic gates, which you know, and we'll kind of go into kind of how they all work in more detail. For now, I'm just going to give us a very high-level picture. The gates universal gate set has to have essentially be able to do any operation on a single qubit, so a single bit, classically. And then it also needs to be able to do one operation on a pair of qubits. And usually the gate that people use is the C0 gate. So, which is a control not. We'll get into it a bit more, but it's just a 2-qubit operation. So the single qubit gates for neutral atoms are awesome. You can kind of use the lasers to control these things. And we'll look in a little bit more detail about why it's sort of so awesome later, but it's all kind of, the gates work very well, maybe among the best out of all of the possible options. The downside, which is not, is that the 2-qubit gates suck a bit and need to be made better. But this is not an uncommon situation for any of the technologies at the moment, but I'd say it's maybe more of a problem for neutral atoms. anyway, kind of really implementing these gates kind of in QuTiP using like real sort of like evolution of the system is where we're going to spend. Maybe I'll put a star here because here's where we're going to spend most of our our time, I guess, for the rest of the tutorial. And here, so like single Qubit Gates tick, 2 Qubit Gates, really active area of research to make them better. Maybe we'll say there's quite a lot that one can do with bad gates. So if you come from any kind of like, if you've done any kind of optimization world or machine learning, actually having some noise in your system can be really useful when you're doing optimization because it prevents getting stuck in local minima or or your system becoming overly sort of optimized to some like particular case. So the fact that you have a bit of noise injected is not an insurmountable problem, but it is a problem if you want to really do like circuit-based quantum computing, the kind of holy grail that people are sort of looking for. Maybe I'll say personally, oh, sorry, yes?
Just on the gates, so, because you mentioned multiple gates working on a single qubit, whereas like in traditional computer science, there's only one unary gate, right?
Yes, not gates,
so,
yes.
Right, so you need like other gates in the qubit land, like one gate to turn it from a state to another, or what, you know?
Yes, so we're going to get into this in more depth, but maybe we can start now. So, okay, so classically, there's only 2 states. In quantum mechanically, I'm going to write down 0 and 1 again, but just in like a slightly fancier way. And then you just put some little like strange brackets around them. Oops. And we'll get more into like what these mean. But essentially, you can read this as this is the state 0, and this is the state 1. But in the quantum case, these are not the only states. So these are, if you've done any algebra, these are the basis states. And then the full set of states is kind of alpha 1, where these alpha and beta are 2 complex numbers. And we'll see later that the squares of their lengths need to sum to 1. And there's also another bit of a strange criteria, which is that you can multiply this whole thing by e to the I theta. So like you can do e to the I theta, and that these are equivalent states. So these are like an equivalence class of these things. But anyway, we'll go into this in more depth, but it is a really good point. Like in the classical case, there is kind of only, well, there's 2 gates. There's one can do nothing. And there's 2, which is kind of invert them. Those are the only kind of operations you can make. In the quantum case, there's, in the quantum case, there's kind of more you can do because, for example, you can sort of swap 0 and 1, which is like not, but that has all kinds of other different operations. So if you just write down the truth table, so this is not, and put it in output. Then the corresponding quantum gate will do exactly the same thing to the basis states. So, but then if you were to look at what were to happen if to this state, so you'd apply not, and because we're using like we'll see these are all linear operations, it becomes that's so like not psi is not 0 plus not 1, right? And then, okay, we can know from the table what those should be. So that's 1 plus 0. So 0 goes to 1, 1 goes to 0. And now we're back at the same state we started out with. So there are states which not leaves, like quantum mechanical states, which not leaves unchanged. And these are actually the kind of eigenstates of the not gate. Right. Okay, good question. I wanted to say, one thing. So, I mean, this maybe, I guess, it paints like a picture of sort of a lot of work to do. But because you actually don't need things to be perfect to do these kind of optimization problems, they're already actually very useful. And in fact, the people who made like exactly these neutral atoms devices we've looked at now have been selected to be installed in high-performance computing centers throughout in Europe. In fact, the EU has bought 2 of them to start with. And randomly, one of them is going to the Jülich supercomputing facility, which is next door to me. It's like in Germany, but I'm in a very narrow part of the Netherlands. So so it looks like people will actually start using them soon. And then the last one is you have to be able to perform measurement on your qubits. So actually you have to kind of read out results afterwards. And we're not going to talk about that kind of a huge amount, mostly because with the we can get the measurements out of our simulation kind of really easily. But we actually will be doing a lot of our work kind of on the actual, like looking at the actual states inside the simulator, like something you couldn't do like in a physical experiment at all. But the downside for neutral atoms with measurements is that they you have to do all of your measurements at the end. So the measurement is what's called a destructive measurement. And what it does is it causes the atoms to kind of emit light, but also ejects them from the traps. And you measure all of the atoms at once. So you shine like a laser over all of the atoms, and then they kind of bounce out, and you get a picture of which ones were in whichever state you're measuring. And it's kind of great. It's quite a simple procedure, and the kind of error rates are low, but it's a bit painful having to only. So there's also a theorem which says you can always move all of the measurements of like a quantum circuit to the end. So it's from a theoretical point of view, it's not a train smash at all, but it is very painful from like a practical standpoint. And it also makes some things harder. The fact that you can't do like a measurement and then change what gates you're going to perform on later is a restriction. Yeah. Cool. So that's kind of where we are with sort of the five criteria and where we're going to focus our attention. So maybe just quickly, I'll kind of end off this little section by just looking at wanting a quantum network. Like, why did DiVincenzo even add in this like quantum network thing? And the answer is that probably as you scale systems up initially, you're going to need to be able to move information from like one quantum computer to like another device next door somehow. And so these two are quite fun. So the one is the ability to interconvert stationary and flying qubits. So stationary qubits are, in our examples, atoms. Flying qubits are almost always photons, because photons kind of like to move and don't like to not move. So I think there's some like reasonable hope. I mean, we're already interacting, like doing all of our interactions with light, so probably it's not too hard to imagine some sort of protocol where you have a photon interact with one of your neutral atoms, pick up some sort of like quantum information from the neutral atoms, and then kind of fly off somewhere else. So that seems good. Yeah, and then some ways to kind of transmit the photons between devices and get them back in. So I think neutral atoms are probably fairly solid on that ground. I'm not aware of anyone actually doing anything in that direction at the moment. People are building quantum networks. Not sure if you know, like China has like a few thousand kilometer like quantum key distribution thing, and I think US and Europe are frantically catching up. So there's a lot happening on the quantum networking side. Partly, I guess there are two big uses. One is just security of information, just trying to kind of secure it. and the other one is probably more related to real science. Like if you can really distribute light around and maintain phase coherence, suddenly you can do like interferometry, like kind of analog interferometry sort of between very distant things. You can imagine like, I don't know, a piece of light coming from a star impacting sort of two atoms and two devices, really bringing those together, interfering them. Anyway, but so exciting, but not what we're going to look at today. Cool. Okay, I'd like to have a little break now. We've been going for slightly longer than an hour. So what I would like to do just before people go on a break, if you can, just open up Jupyter and whichever Jupyter you used, hopefully to run the little test notebook that I posted in the instructions. And yeah, just kind of get that open because we will sort of look at that a little bit next. And yeah, and then we can have a short break. And I don't know, how long a break do people want? Like 5 minutes, 10 minutes? Okay, let's kind of get back here around in 5 minutes or so, and we can see where we are. And if you're a couple of minutes late, that's fine. Okay, so I wanted to start the next section by just giving, like, and you're actually welcome to sort of type in your, like, some of these things into your notebook just so you kind of have them kind of look at, but don't necessarily try and type all of them. So yeah, just some imports at the top. So we just, I mean, QuTiP, and we mostly use NumPy for the value of pi. But some are also useful for like cosines and sines and things. And then we use matplotlib for plotting. And then what we're going to try and do in the rest of the tutorial is fill in this little neutral atom circuit class. So what maybe I will kind of quickly scroll down to how you use the class, and we can go back up. So so you pass in a list of atoms and just kind of their positions. So this is just like an atom, one at the XY coordinate, like 1, 0, and the other one at 1, 0, 1. It's just like kind of opposite parts of the square. And we pass them into a neutral atom circuit. And then we can run, the idea is we can run little circuits by, so there are 3 gates which are single qubit gates. And they're called RX. R stands for rotations. There's a rotation about x-axis, rotation about z-axis, rotation about y-axis. And this 0 sits on the first qubit, so on qubit 0. And then this pi over 4 is what angle to rotate through. And we'll kind of get to all of that, like understand it all a bit better. And then we can run a, we can run a circuit which includes this CZ gate, which is a controlled phase flip, which also we'll get to in a bit. And we'll use that to implement a C0 gate. So that's the kind of this controlled NOT, which we'll also get to in a bit. And then we can plot all of our results nicely, and kind of look at what's happened. Anyway, but we'll have a little kind of class that we can use to run these circuits. Okay, so you can see here there's these 3 single qubit gates, the 3 rotations around 3 different axes. We'll get to that in a bit. There's this gate H, which is called the Hadamard gate, which we will also get into a bit. Its action is just to take our state, the state 0 gets so if we write down its kind of actions here, the Hadamard gate usually represented confusingly as H, which is also useful, like the Hilbert space and the Hamiltonian. It maps the state 0 to the state 0 plus 1, and it maps the state 1 to the state 0 minus 1. Okay, so it is, and then it also happens to be its own inverse. So if you just plug in all of the linear over, you'll come out. If you put in 0 plus 1, you can see the 2 zeros will add, and the 2 1s will cancel, and you get 0. And then when you put 0 minus 1 in, then the 1s will add, and the zeros will cancel. So, awesome. So that's the Hadamard gate just implemented because it's very practically useful and it's just kind of used a lot. And we can implement it in terms of our Rx, our Ry, and our RZ gates. And then there are two qubit gates. One is this controlled Z, which we'll kind of get to. What it just says is if the control qubit is 1, then flip the phase of the target qubit. So that'll essentially introduce a minus sign into it'll change here. It'll change beta to minus beta. And then run will be the thing we actually use to run our circuit. So write down even if you just write down class neutral atom circuit, and you cannot leave everything else for later. Just have something to remind you what we're doing. Cool. Okay, so we actually kind of covered a little bit the most introductory, what is a qubit, kind of earlier during our question. So just a reminder, kind of classical bit, states 0 and 1. A quantum bit has basis states 0 and 1. It sounds almost exactly the same, of course, except that basis state implies that there's a kind of whole sort of linear combination. Well, maybe actually, let me just quickly. Maybe actually, let's just see, in your notebooks, just how to create these basis states in Qubit. So in QuTiP. So if you type in B0 equals QuTiP dot basis 2, 0, what that says is, please make me a basis state. It says there are 2 basis states in total, and I would like the 0th basis state. And then you can print it out, or just let Jupyter automatically print it for you. And you'll see it prints out a. Also, shout, do I need to make this a bit bigger, or is it fine?
A bit bigger would be great, actually.
Cool.
Just because of the light that's shining on it, it's not your fault.
Yeah. Cool. So when you print it out, you see a nice representation. Maybe you can start with this quantum object data bit. So this is just a little. So we know that we're taking linear combinations, so not be too surprising that we see our state is represented by a column vector under the hood. So this is kind of the basis vector that QuTiP is using to represent our basis state 0. And it's the state kind of 1, 0. This shape thing at the top here, this shape equals 2, 1, that's just the NumPy array shape of the underlying data. That just says it's a kind of convector with 2. Okay. The type is type ket, which means which just means it's a quantum state. Maybe we can just quickly do where the strange word ket comes from. So when you do effectively the dot products of, so if you want to, if you have one, so you write the state like this. So as we've been doing kind of sort of all along, it's a sort of straight bracket. The reason that we write it like this is that we write the inner product. So the inner product of the 2. So that's just a NumPy is just kind of the 1, 0 kind of dot products kind of 1, 0. So as we'll see in a second, so this is the convector, and then this will be the be the row vector for the same thing. But as you'll see in a moment, we tend to work with these row vectors and column vectors separately quite a lot. So what Dirac did, famous physicist, was he just split this in two, and he said, like, okay, well, this is like my state 1, 0, and then I will use this other part as the row vector, and together these are a bracket, and then, so this is the second part of the bracket, and this is the first part. So the bra is the first part, and the second part is the ket, and there's like a missing C in the middle. Anyway, it's like a bit of a silly pun, but it's also kind of very useful to have like simple words for describing these things. So ket means it's a state, and in our case, a column vector in our representation. And you'll see that in addition to bra and ket, you can also have a few other kinds of states in QuTiP. Sorry. DIMS is short for dimensions, and the dimensions are, at the moment it's not interesting. It just says it's dimensions 2, 1, which looks a lot like the shape, but written out in kind of a strange way. But what happens in QuTiP is that, so if you have just one qubit, so one neutral atom, then your dimensions are like the ones we see now, like that. But if you have two qubits, then you would end up with 4 basis states. So you would need to have a 4 here. But in QuTiP, if you really had 2 qubits, it would write this as like 1 qubit. 2 qubits, it would look like that. So it would be 2, 2, and then to get the full like size, you would have to multiply the 2 2s together. And then if you had 3 qubits, it would be 2, 2, 2. So it would be 2 thirds. It would be like 2 like n times. And that's just very helpful physically because it helps you understand the structure of the like underlying physical system. So in some sense, like this is identical to 4-1. But when you're working with a system, you might, for example, say, like, I want to know about the state of qubit 1 or qubit 2, and then if you had 4, there would be no kind of organization to the system. So, yeah, so it encodes similar information to the shape, but kind of split up to tell you about the structure of the system. Yeah.
Can you explain again, sorry, the arguments to QuTiP.basis? So why is there what's the 2?
Oh, so the 2 is the number of bases, the total number of basis elements.
Right.
So in our case, we just have 0 and 1.
Right.
But actually, in a little bit, we're going to have 3. So, yeah. Yeah.
And the 0 is just the state that.
Yeah, it's just So if you have 2 basis elements, then your possible like states are the 0 states of the first one, and then you have 3. It's 0, 1, 2, and yeah. Cool. Okay, so now you kind of understand kind of how QuTiP stores these things, so you can also just print out, like, if you need to know the type by itself, you can just do like b0.type for the state or something, or the shape or the DIMS. Yeah, and then if you look at so B1 here was just the second basis element. It's exactly the same, except now it's 0, 1. So you can, I mean, this is just if you were given like a math problem and your basis elements like E1 or E1 through En, then the simplest sort of like representation you could come up with them is just to make a pile of vectors which had 1 in each of the different positions in the vector. And that's exactly what we do inside QuTiP. Okay. Oops. Cool. Maybe let's maybe let's hop back to our kind of unusual atoms a bit, because, okay, great, we know how to write basis states in QuTiP, but what actually are, like, we've just constructed these vectors. What do they actually represent? So as I mentioned, the atoms in our kind of neutral atom device, so inside that little vacuum chamber, are usually kind of alkali metals, and most typically cesium or rubidium, and we'll just focus on cesium for concreteness, really. And I think it's actually the ones used in the array that we saw. Okay, so atomic number 55. So there are in total 55 electrons and 55 protons, and then in total 133 what do you call protons and neutrons? Something like drawing a blank. Anyway, like 32 protons and neutrons in total inside. And one of the things which is kind of great about cesium is essentially it occurs only in one isotope, which is like a small win, but it means that all of your atoms are like slightly more identical than they would be inside your quantum computer that you're trying to build. So that's great. Yeah, and then if you look at the arrangements of the electrons, you can see that these are the kind of electronic orbitals starting from kind of 1, which I guess is sort of the smallest, and going all the way kind of up. And you can see in the outermost orbital, like the first one, there's just one electron in like the 6th sort of set of orbitals, so there's only 1 in 6s. And yeah, and kind of an ionization energy of just 3.89 electron volts roughly. If you are dealing with like any sort of kind of physicists who just spend all of their time working in with these kind of like atomic systems, you'll see they'll give the energy in like centimeters to the -1. And the reason for that is just kind of if you kind of work in sort of in these kind of natural units where you define kind of h bar to be 1, then various strange units get identified with each other. And so centimeter, like inverse length, is in fact a unit of energy. But yeah, just do not be too well. Do not be like me. I was like, what's going on? Like, do I even have the right number? But yes. Okay, so maybe where did I? Let's come back to these plots in a second. I should maybe put them further down. Okay, so here we have just a table of the ionization energy of the outer electron. So this is just, so we're starting here with just kind of 6s. That's the lowest sort of energy level. Kind of, you can see energy level 0. Because it's the lowest energy state that electron can be in. It can't be in any of the lower states because they're all filled up by other electrons. And then if you move it up like 1 level, it goes to the 6p level, where it has slightly higher energy. So now it has like 11,000 like centimeters to the -1. And there's actually 2 different states available in the p states. There's one with like spin 1/2 and one with spin 3/2. We will not have to kind of worry about this too much. But I think what I want you to just see, and we'll see this in the plot in a little bit, the energy levels kind of increase, but they start increasing more and more slowly. So what happens is that the energy levels get closer and closer together as you get kind of further and further away. And eventually there's some level where it just leaves the atom. So this is its kind of ionization kind of limit. And so kind of the last energy level is about kind of 31,000. So it's quite difficult to see that. So maybe let's just look at, maybe I also need to think, like, I'm just going, did I make this, does this one get bigger at the same time? Nope. Maybe it's bigger. Okay. So here are all of the energy levels that we kind of looked at before, but I've just actually broken them out by their spin. So that's just so that they overlap a bit less and a bit clearer, but you can imagine them sort of all be stuck up together. So here at the lowest energy level is the state kind of 6s, so that's just in the outer electron in its lowest state. And then what happens when we kind of shine a control laser on it is that we can add kind of energy or subtract energy from it and move it between these different states. So if we were like real experimentalists designing like a device like this, we would want to pick states that worked well for us. So just kind of looking at this, we can say pick the states, say 6s and 7s, for a few reasons. One is that they're kind of nicely sort of separated from each other, because you don't, if the energy difference between two states is too similar, then you might move the electron kind of between both. You can only essentially select the energy difference that you're supplying by choosing the wavelength of your photons. So if two energy differences are too similar in the drawing, then you won't be able to control those transitions separately. So they're widely separated, and the energy difference is not kind of too similar to any of the other energy differences that they are. You can just sort of, if you just sort of eyeball it, you can see like, okay, there's quite a big gap there. There can't really be that size gap anywhere else, because like there's not enough sort of space like left before you ionize the electron. Cool. So when we're creating our basis states here, so we can just say, okay, state 0 is 6s, state 1 is 7s. Actually, I mean, this is fine for now. It doesn't make too much difference. When you do this, often actually they choose 0 to be the 7s state and 1 sort of to be the sort of 6s state. They might not choose exactly these states, but they might often choose 0 to be the higher one. It's just kind of a matter of convenience. I'm mostly telling you so you don't get confused if you encounter this. Cool. So maybe I want to just go back to this other plot. So I think one thing I wanted to just point out is where these low energy states are in the kind of overall picture. So here, the dotted blue line is the potential well that the electron is experiencing. So that's the attraction from the nucleus minus the repulsion from all of the other electrons. So it's effectively the attraction by sort of a net 1 charge. And the shape of this potential well is not the actual shape. I cheated a bit with the formula just to make it like more apparent on the plot. It's actually kind of quite a bit sort of like steeper. But these sort of 6s and 7s states are the points they're kind of right in the bottom of the potential. And that's important for two reasons. One is it means they're not like likely to accidentally get ionized and fly away. But also it means that their position is more confined closer to the center of the atom and thus further away from surrounding atoms. So if you then just look at this plot here, we can see, so remember that as we get higher up the potential well, the states get closer and closer together. So I've drawn sort of 3 states close to each other, and you can see there the potential well is wider, so there the states are more sort of distributed, and you can see that it kind of like, they get sort of exponentially wider as you get closer to the electron being kind of completely ionized. And this effect of the kind of electrons kind of moving sort of away from the atom as we kind of drive them up is how we're going to get 2 qubits to interact. like two neighboring atoms to interact. Okay, does that all make sense so far? Yeah, okay. So maybe let's see if there's more to look at here. Okay, so okay, let's talk about how the two-qubit interaction is going to work a bit, because that's why we will in fact need 3 states rather than 2. So now let's look at where do we okay, this is just kind of how the distance varies with atomic number n. So the n is like the 6s and the 7s. So you can see as you go up like 6, 7 kind of higher, it goes up as n squared. And because you kind of can make that sort of number almost as large as you like, it's kind of n squared is going to be quite big once you get quite high up into the kind of number of sort of the of like which the count of which energy kind of level you're in, and then hello. No, okay, we'll come back. I think we'll be fine. You'll see once we get back to the code. You haven't missed too much on the code side. Okay, so what are we looking at here in this plot? So here, so what we're going to do is we're going to select one of these very high energy states as our third state that we're going to use to get atoms to interact, and then we call this high energy state R. So we can have either 0, 1, and R as our 3 basic states, or A, B, and R, or whatever you want to call them. And now these states RR means that both an atom and its neighboring atom are both in a very high energy state. And then this is the energy of interaction between the electrons in that state. So you can imagine that you have 2 neutral atoms here, and then now kind of they're both in the states where sort of the electron cloud is not to scale, it's back further away. So this is like E, and then as you kind of depending on this distance here, it's confusing. I'm also going to call R. There is some kind of energy associated with these electrons being close to each other, so now this is an actual like real diagram with kind of actual. This is actually the shape of the curve. So here, when the atoms are far apart, you can see that the kind of energy of interaction is kind of relatively kind of like constant and kind of low, and there's no real interaction sort of on the right-hand side of the picture. But then you can see as you bring the kind of atoms close together, the sort of energy of interaction sort of goes up very quickly, and is almost a kind of wall. And this wall in energy is called the River Blockade. And what it means is that if you imagine that we had a sort of a small like laser sort of that could push the states, that one of the electrons into this R state, then if we try to push a neighboring like electron, like a neighboring atom's electron into that same R state, it would be prevented because this kind of this energy of interaction. So so this kind of River Blockade effect, where you get a very strong interaction between 2 neighboring kind of atoms, or at least the electrons of 2 neighboring atoms, but only when they're both in this very sort of like high end, sort of far from the nucleus state, is what we will use to kind of generate a gate. So we will kind of either move or not move some states kind of into this sort of R state, and then there will be a situation where the 2 neighboring atoms are prevented from both going into the R state, but they can easily go into the R state if only one of them is doing it. Yeah.
So this is what you were saying before then, where you basically put one atom or two atoms into the R state, so now you have these two electrons blockading up against each other.
Yes, yes. You put two. Well, you prevent it from putting two, which is what gives you the interaction.
Right. So they're interacting. So now let's say you're trying to do that CZ gate, right?
Yeah.
Does that action implement the CZ gate, or now once you have these two electrons interacting, then you apply another operation that then?
Okay, maybe I will just show the drawing of the protocol, which should now be understandable. So, where is this? Is this is sorry. This is from an actual paper. Just because I'm too far on the bottom of the paper. That's fine. So this is the actual protocol for maybe. Let me just. So this drawing on the right here shows the actual protocol with the 3 states. So let's just concentrate on the top left block for the moment. So in the top left block, we have so you can see two atoms side by side. So the control is the left atom and the target is the right. So the control, yeah. So I maybe don't want to go through this completely now, but so what you do is you try and move the control from the state that it's in, and in this top left block, it's in the state 1. So you can see there is the yellow dot on the state 1. You try and move it up to this R state, but that fails because you put in a laser pulse which would only drive the state 0 into the R state. So nothing happens there. And then what you do is you drive the target QuTiP into the R state and back out, which what gives you kind of the phase flip that you want. And then if now we move to the right, where now the control, it's the same situation, but the control qubit is in the state 0. Now the first laser pulse drives the control qubit into the R state. Then the second pulse, which would drive the target, which in the previous drawing would have driven the target into the R state, fails, because now the energy required is gap is much bigger. And then afterwards you drive the control atom back down into the 0 state where it was. And then a similar thing happens for the others. And this kind of interaction means you get sort of 3 cases where you can drive one of the atoms into the R state, and one case where kind of none of them kind of get driven into the R state. And the fact that that in one case, this case where they're both in the state 1, the fact that nothing happens in that case is what makes that case different, and that gives us the interaction we need. And maybe we'll come back to that in a little bit more detail later. Okay, let's actually, so maybe let's now go, maybe let's keep our 2 states for the moment, so we can visualize things. But yeah, or maybe actually feel free, let's actually go back and actually make our states, we can call them like A, B, and R, or B0, B1, BR, whatever you want to call them, but now put in a 3 instead of the 2. And just kind of quickly make kind of like state 3.0, state 3.1, and state 3.2, and those will be the 3 states that we work with for the rest of the tutorial. Cool, and shout when you're happy to go on. Good. Okay, great. Okay, so now let's keep our, maybe also make another like B0 and B1, which is just the original basis, unless you, or maybe you already have them, because we're going to look at how we build up these the kind of linear combinations of states, these alpha 0 plus beta 1. And maybe I'll kind of just reiterate again. So the alpha squared and the beta, well, the length of alpha squared plus length of beta squared have to sum to 1. But actually, QuTiP will take care of that for you when you tell it to do, and we'll see in a second how. So don't worry about it for now. The other thing that the fact that kind of these states which have this which just have two states which are related by being multiplied by e to the I theta, so some complex number with length 1, are the same state. QuTiP doesn't take care of for you, and there's a very good reason for that, which is that if you have just one atom, so 1 qubit, your state is written like this. But when you have if you add a second qubit, and we'll see how to write that in a bit, so it'll essentially be combined, there will then only be a single global phase for the whole system. So whether or not you want to keep track of this, whether these states are really physically the same, depends on whether you're considering an atom to be really just a whole system by itself, or part of some larger system that you happen to be manipulating separately. Cool. So I think now this actually just prints like a few things which sort of show kind of what happens when you multiply these different states. So you can multiply one by like complex number, like 1j, or you can just add B0 and B1, subtract them, and I guess you see sort of all the kind of the kind of obvious results. So now you have a state which is kind of 1j, so it just has like I, well, yeah, kind of I and 0. It's now slightly more difficult to read, and of course that state is actually the same physical state as B0 was, because it's just multiplied by some phase constant. And then we can kind of add things together. So, okay, so the reason that these alphas, this kind of alpha squared plus beta squared, have to sum to 1 is that if you were to kind of measure whether this state was in state 0 or state 1, so kind of detect whether, in our case, whether like a photon had been emitted or not, then the likelihood of kind of seeing whatever is supposed to happen in state 0 in your measurements is alpha squared, well, the length of alpha squared, and the likelihood of seeing whatever is meant to happen in state 1 is beta squared. And since all of the states, I mean, those are the only two states, one of those two cases must happen, so it must sum to 1. Yeah, so that's kind of why we need that. Okay, so obviously it is quite important to sort of normalize the states that this is true. And so let's just kind of have a look, I guess, at the next bit. So you can type, if you have a state, say psi, which is kind of B0 plus B1, you can use .norm, and then it will print out the length of the state for you. So it'll just kind of take the dot product and square root it. So this is kind of 1 squared plus 1 squared, which is 2, and then square rooted, which is like 1.414. And then if you were going to normalize the state, you would divide it by the norm. So you divide it by psi norm, or multiply it by like 0.70. But QuTiP also just has this handy function .unit. So if you call .unit, it will just return the state divided by its norm, and now your vector looks kind of less nice, but you can still you sort of get used to just seeing these numbers cropping up whenever you're doing the right thing. Yeah, and then kind of when we were talking earlier, I was speaking about, so these are kind of this being sort of the kits, and that being kind of the bra, and together they form the kind of inner product. So there's a way in QuTiP from getting from a kit to a bra, or from a bra to a kit, and that's just, so if we just had real matrices, it would just be the transpose. So, but because these are complex matrices, it's actually the transpose followed by taking the complex conjugate of each individual element. So you also see it called the adjoint. You can see why that will be the case. So if our state coefficients are alpha and beta, and we want to get the norm, then if we were to just put alpha plus beta there, we would get alpha squared plus beta squared. But of course, alpha squared might still be some complex number, it's not some real number, it's not the length of alpha. So we have to just take the complex conjugate of each of those, and then we've got alpha times alpha complex conjugate plus beta complex conjugate. So that's good. And QuTiP has a method for doing this transpose plus complex conjugates, which is just called dot dag. So if you have a kit and you do dot dag, you get a bra. If you have a bra and you do dot dag, you get a kit. And dag is short for dagger, which is just, if you read the academic papers, you'll see it written as like psi dagger, or like psi plus, because this little like elongated like footnote symbol. Cool, and maybe just if you do like v0.dag, you'll see that this type comes out as bra, and otherwise it's kind of, and it's a row vector, and otherwise it all looks kind of very familiar. Good. Okay, so maybe here, like, okay, we've done inner products, we've done sort of, so we know what a bra kit is, but maybe now it's, but in quantum physics, you also use kit bras a lot. So that is written like this, right? But what is this? And it's exactly what you would expect from kind of normal sort of, and then so that's, and then you just multiply this out using normal matrix multiplication. So it's 1 times this row, so it's 1, 0, and then 0 times this row, so that's 0, 0. So that's 1 times 1, 0, and 0 times 1, 0 units. So, okay. And you can do that in QuTiP quickly, and it will kind of do it for you. And yeah, so you get this, whoops. Yeah, you get this kind of operator here. What does it actually do is, I guess, kind of a question. So how to read these expressions. So, like a kit just means this is a state. And then you read a bra as kind of give me the components in the direction in the direction psi of whatever it's acting on. So if you were to write, let's like our state 0, or maybe it's actually better if I do it. Oh, let's do it this way. So this says, what is the component of the state 0 in the direction of my state psi? So this is like, what is, well, the component in, I'm running out of spectrum in the right directions, psi. So, and now you can, so now you can read the norm using that. So it says, give me the direction of the state psi in the direction of psi, which is just its length. So yeah, give me the component of psi in its own direction, which is length. And then what is, and now we're in a position where we can finally read this. So this is just an operation that we apply normally as we would function. So it says give me the component in the direction psi, and then multiply it by the state psi. Or you could generally have another thing here. So it says take the component in the direction psi, and then that just gives you a number, and multiply. Well, yeah, a complex number, and then it says, and then multiply the state phi by that number. So it's just a kind of, it's just a linear operation which takes like a projection in one direction and then maps it to to another direction.
So I'm sorry if I missed that. So when you have that, so the inner product is like a dot product, so I understood that. The outer product, like you have the Braun and Kent like reversed like that.
Yeah.
What does that give you just mechanically? Does that give you like a 2x2 matrix, or is that?
Yes, yeah. So it gives you a linear map from vectors to vectors.
Got it.
And yeah, the way it does it, if you have this, is it's do a projection onto the state psi, which gives you some number, and then multiply the state that you're sort of projecting to by that number.
Okay.
Okay, this is just looking at, so one thing that is a kind of an important gotcha because of this fact that there's this global phase that could be in front. If you just take some vector b0 and then multiply it by, by like 1j, or just like, I don't know, like e to the I pi or something, it'll give you a new state b0, which is by construction equivalent. But if you compare them equal in QuTiP, it'll tell you that it's false, isn't they're not equal, which is true if you're not considering them as being the entire system, if you're considering them to be a part of some system. But how do you check if two states are already the same physical state? So the way that you do that is by calculating the overlap, which is in fact just the inner product between two different states, not psi and psi, that's like phi and psi. And that overlap you can show is only one if the two states are identical. And so if you take the overlap of like B0 and B0 rotated by some phase, that's that overlap will be 1. What's a little bit confusing here, and this is also worthwhile pointing out, when you do these kind of calculations in QuTiP, you will get out you'll get out like a complex number buried inside like a matrix. So you have to kind of fish it out, which is a little bit annoying. But anyway, so this is how you kind of calculate it. Okay, probably, especially if you've done this the first time, like you sort of know, I guess, algebraically, like, okay, these are linear combinations. The alpha squared plus b squared must sum to 1. I must remember that the things with the same global phase are equivalent, but you probably have no idea like what this state space actually looks like. But luckily, there is a really nice way to visualize these things, which we can kind of try now, called the block sphere. And so the idea so the idea here, and you can kind of see that you can capture the fact that the lengths have to the squares of lengths have to sum to 1 by replacing alpha and beta's magnitudes by a sine and a cos of some like single angle, because then you have sine squared plus cos squared equals 1. So that takes care of the, so if you write phi as like cos of something plus sine of something, then you know that alpha squared plus beta squared is going to be equal to 1. So now you've removed that whole, you've taken care of that constraint. And then you know that only the relative sort of phase is important. So you just write a single phase in front of, so you just arrange for say the constant phi to be a real number, just kind of like rotated by the right phase. And then you only have the difference in phase for beta. And so that's kind of e to the I phi. And now you've got sort of two angles, right? You've got theta and phi, and it's starting to remind you of spherical coordinates. It is not exactly the same as spherical coordinates because of this this need to divide by 2, which is an important technical detail, but it's not actually going to affect us now. It just means that the structure of the space means that the kind of angle kind of is that you rotate through kind of moves sort of like twice as quickly as you would expect. But I think the important thing now is to plot this for yourself in QuTiP. So you can make, if you type qtip.block, it gives you this like, so this representation of the space of, like the space of all possible qubit states on a sphere is called the block sphere. And it's like an extremely useful tool for telling like what is going on with 2 qubit states. So here, like after you've created the block sphere, you can just add whatever state you like. So here I just added B0 and B1 and just add them with this add states method and just give it a list. I set the colors explicitly. This is a bit of a wart in like how QuTiP works. The block sphere implementation is very old, and actually one of our Google Summer of Code students from last year is busy slowly fixing it up for QuTiP 5, which is the next version of like the next major version of QuTiP. So hopefully it'll get less clunky. But for now, you just set a list of colors, one for each state that you want. And I like to do this mostly so I don't get confused about which state is which. So I know that R is like red is the first state and blue is the second. And at the moment at the end you call block.show, and then hopefully you also get kind of arrows pointing in the right directions. Cool. Maybe get your pictures up and give me a thumbs up, and then we can just talk through kind of the important things here. So I think there's a whole bunch that we can learn from this picture. So firstly, the 0 basis state is kind of normally at the North Pole, and the 1 basis state is at the bottom, so the South Pole. And importantly, note that they're not orthogonal in the ordinal, like geographical sense here. They're orthogonal in the space of in the qubit space, so in this 2-dimensional Hilbert space we constructed. So like 0, kind of the overlap between 0 and 1 is nothing, but they don't appear orthogonal on the block sphere. So that's just something to kind of keep in mind, because you can't understand orthogonality from this picture. And we'll kind of look at some more states in a bit. But also you can see, so this X and Y axis. So remember I said that we're going to implement rotations around like that Rx and that Ry. So those rotations are about this x-axis. So the Rx is a rotation about x-axis, Ry is a rotation about the y-axis, and then the z-axis is the north-south one. So rotations around the z-axis are just like spinning the basketball. And now kind of you can also see why the rotations are kind of all of the 2-bit all of the qubit operations that you can do is a rotation of some sort, because those are the only kind of movements that you can do around the space. So given an initial state and the final state, it can always be expressed as a rotation of some sort. We're going to implement kind of all three kinds of rotations, just because it's a little bit less kind of head scratching, but you can get away with two. And in practical implementations, you often well, it kind of actually depends on the physics of the problem. If it's easier to do two and it gives you like better results, you do only two. If it's easier to do three, you just do all three. So.
Can we not plot a sphere for 3-state qubits?
So maybe I should say one of the very unfortunate things about quantum mechanics is that there's no good visualization for 3 states or anything like anything above that I know of, and we will actually see some of this here. Often what I end up doing is I end up kind of reducing, essentially extracting like only part of the state, and just getting just looking at the relationship between 2 states and then plotting them on the block sphere as though they were a 2-state system. More generally, if you've got even more states, you just start looking at kind of different projections of your states, trying to measure the amount of entanglement between things. It all becomes kind of very sort of challenging and case specific. Okay, one of the cool things now is you can just kind of like plot a whole bunch of states at once, which all are just related by global phase. So here I've just taken B0 and just multiplied it by kind of e to the I times theta, from theta in 0 to 2 pi in like just some steps. And you can see they all end up just as one line on the block sphere. And to convince yourself that there's not like some problem with the implementation of the block sphere, you can do the same thing, but now you put in a phase between B0 and B1. So you have B0 times some phase plus B1, and now you actually see kind of 16 kind of arrows. So here, B0 plus B1 ends up on the just along the x-axis. So this, so this is that state where that on the contour of the x-axis is the state 0 plus 1, and then these just kind of rotate the phase around the block sphere. Good. Cool. Everyone happy? Block sphere's going nicely. Cool. Okay. Let's see if there's any. Okay, good. Cool. Okay, I think what we should do now is actually to start by trying to implement kind of this state function, and kind of what we want is just so maybe I'll actually just find a little place to play. Oops. Maybe let's do it here. No. Okay, let me just quickly execute these so I can. And what we want actually is to be able to call something like, so we want to have a function where we can just, and we'll kind of see why we might want a function to do this, especially if you're dealing with lots of qubits. But we want to just return something which is this, like the first atom in the state 0 and the second atom also in its own state 0. So 2 atoms come side by side, electron, say one electron in state 6s, the other electron in state 6s. So we have to kind of learn how to represent this. And so let's just make, so I'm just going to make, we won't actually have to do this, but I'm going to make, what do we call this? Let's call them atom. So this is the state B0, but for the first atom. So, and I'm just going to do it with 2 basis states to start with. Yeah, okay, well maybe then, yeah, let's do it like that. And then I'm going to make the second atom, and so that's how we represent the 2 atoms separately. Now, how do we get the combined state for the whole system? So I'll just call this B00, which is kind of both of them in B0. And there is the operation called QuTiP.tensor, and that takes a list, and you just give the list of the systems you want to combine. Oh, and let me just okay, so that is how you like type it in QuTiP, but what actually has happened here, and what is this tensor product thing? Maybe let's make some space. Okay, maybe something. Also, maybe this should also be a bit bigger. Okay, so I think first of all, let's just look at what QuTiP produced. So we can see here the dimensions are 2, 2. So that means we have 2 systems, each of which have dimension 2 that have been joined together. And there are 4 basis states, and the kind of reason, so yeah, and you can see there are 4 elements. So that means there's 4 amplitudes, so there's 4 basis states. So the basis states correspond to exactly the 4 basis states that you would. I mean, if you just had a classical system, you would have 0, 0, 0, 1, 1, 0, 1, 1, and these are in fact again the same way when we created the space for when there were 2 basis states, where we just created a state for each basis state. Exactly the same thing happens here. Those states are often named things like, and now there's the general state is sort of like alpha 0, well, actually 0, 0 plus 0, 1 plus alpha 1, 0 plus alpha 1, 1. Okay, so that's the most kind of general state now. So there's now 4 amplitudes. Again, the 4 amplitudes still have to sum to 1. You can still use QuTiP like .unit if you need to sort them out. And there's now, again, kind of 1 global phase. And now you can kind of see why QuTiP didn't handle the global phase for us, because there might be like an important phase difference kind of within some of these states that are kind of important. Because now, before there would have been 2 like global phases, and now there's only 1. So, good. Okay, so yeah, how much sense is this making? I know for me, just like thinking through why you get out this kind of sort of structure. It's like I feel like the more I dig, the more sort of like I ask questions about why things are this way. But yeah, people kind of happy with at least the construct for now. So.
There's a lot I'm going to dig into later on, but
yeah. Cool. Okay. So now, what we would like to do with our state function is to be able to write something like the state 0, 0, and to kind of get out like an actual like QuTiP state. So maybe let's just run through the different kind of combinations. Let's look at 0, 1. So 0, 1 is the second state. 0, 2 is the third. So yeah, it's all just like happy binary kind of like indexing. So okay, good. Maybe I'd say it's also notice here that here we could write this state 0, 0. But imagine we had a state. Well, actually, let's just make it. Let's just make. Let's just make. So, well, these are now 1, so I'll just make this 1. And I'll just. And let's make these again. And then now we can make 1, 1. Okay, okay, good. And then, okay, now it's just, well, okay, let's just print B1, 1 again, okay. Okay, so that's, we know, but now let's add them together. So this state, which is like just 0, 0 plus 1, 1, is called kind of the Bell state, and it has this kind of interesting property that you can't write out, you can't find. So if you have the state 0, 0 plus 1, 1, there isn't. It's not equal to, say, it's not equal to, say, some state psi tensor product, some state phi, for any psi or phi. So there isn't a way to write it as two. There's no longer any way to write it as the state as two separate systems. Now they're just kind of, you can only think about the whole state, and if you ask questions about kind of one of the particular parts, you get out only probabilistic kind of answers. All right. You also see these tensor products written like just next to each other, which can be very confusing if you're kind of not used to it, and you see a big complicated expression, and it's like, oh, this just looks like multiplication. And then sometimes you'll see things written like this. So yeah, so this is just the tensor product symbol. So yeah, this just combine. Yeah, this just says tensor product of those two. Yeah. If it's going to be confusing, I recommend, like, if you're writing complicated expressions, just be a bit more explicit for yourself. Otherwise, it can get hard to figure out what is going on. Okay, so I think so you can see now from all of this typing, while it would be nice to have a function which would just make these states for us, and not a very difficult function. So we can, I don't know, just make a list of states which starts out empty, and I don't know, for like each character in S, I don't know, if it's 0, then we do like Q. Well, let me just do, maybe let's just call this like states or something. And then if C is 0, we do like, we can just call this Q equals oh, sorry, this is a bit too indented. And then it's also actually useful sometimes to do like and then you can do like here, and then then you can do like states, and the states dot append q.unit just to normalize everything afterwards, and then return QuTiP dot tensor states. I don't know. And now maybe this will even work. Who knows? Okay. So then we can do things like 0 and 1. Oops. Oh. Missing some eyes. Okay. Okay, so yeah, maybe just can give people a few minutes. Meep. Cool.
Sorry, so what does 0 plus mean?
Yeah, so I left it up because this is like where one of the points where things start to get a bit more confusing. So, okay, so 0 plus means the tensor product of the state 0 with the state plus. Okay, so so what does that mean? So now we just write everything out. So that's 0 plus 1. And then I'm actually going to write over here just the factor of like 1 over square root 2, which we need. So that's just to normalize the state. Now, so there's actually like a tensor product here between these two. So the tensor product is linear in both of its arguments. So we can just multiply like this out. So this becomes 0 tensor 0 plus 0 tensor 1, all still times 1 over square root 2. Which if we just write that slightly shorter, it's 0, 0 plus 0, 1. So, and now you can see why QuTiP kind of outputs what it does, because you can see that what its output is. So this is the vector just 1, 0, 0, 0, and this is the vector 0, 1, 0, 0. Yeah, so, and then just the vector of square root 2. So, yeah, so that's what 0 plus is. It's the tensor product between the state 0 and the state plus. And you can imagine that things get sort of, yeah, so now that's kind of, you've just had like all even combinations. So, okay. So one question is, how do you visualize what is going on here? So let's just call this state, I don't know, 0p or something for like 0 plus. And then just save it. Okay, so so how do we know what's going on? So there's an operation called the partial trace, and I don't want to go into too much detail about it, but what you do is you just sum over sort of kind of all of one part of a system, and you're left with just another part. So it's a way of like separating this whole system back into two pieces. So we can do equals, so I just remember this goes. And now we're going to say we want to keep, actually not sure if we need, well, do we need brackets? I'm not sure. Anyway, so we want to say we're just going to keep the first qubit. So now what we get out is a thing called a density matrix, which this density matrix happens, so we'll get maybe a little short description of what density matrices are in a little bit, but they're another slightly different way of representing representing states. And now we can do and then we do okay. So what is great is that we can see that that the block sphere can just render these density matrices as though they were ordinary states. And I'll talk a little bit about what density matrices are in a second. But let's just also maybe look at the state of. So now we'll keep. So again, take the combined system, so B0 plus, but now we'll keep the second. Whoops. Now we'll keep the second state rather than the first one. So let's keep the second atom rather than the first one, and then now we'll plot both. Okay, so now you can see that the first atom is in the state 0. So and then the second atom is in the state plus. If we quickly run this again, but let's do one of like the awkward states. So yes. Now you can see they're gone. Oops. Oh, I didn't. I know what's happened. So we need to make this a unit vector. So I didn't normalize them afterwards. And that's what's happened. Okay, it's better. Else. Not. Okay, I do not know why that's not working. Maybe I'll have to. I did it a slightly different way. Let's just look at. Anyway, okay, maybe the important point to take home here is because if you can't separate the two states, then this whole procedure of using the trace to visualize things on the block sphere becomes more tricky. And the states are just the same. Okay, so we now have kind of a state function and some way to visualize it. Awesome. How are people? Because I realized quite a long time since we took a break. How are people doing? And do people want like a 5-minute break now, or do people just want to continue? Cool. Okay. Cool. Let's do that. And then maybe when we come back, just a little bit worried about time. Maybe I will kind of, I guess, kind of work. Yeah, we can start working through how to implement the kind of rotation gates and things, and see how far we get. Actually, maybe also. Yeah. Anyway, let's take a break, and then we'll kind of leap back in afterwards.
It's cold in here. It's 69 degrees.
Ah, we want to put it upwards and find either way. It's just how it was.
Freeze us out of this room.
Sorry.
Outside. I thought I was getting sick or something. No, it's just really cold.
So when it comes to like many body systems, what's kind of the upper limit that people have been able to simulate in QuTiP?
It comes down a lot to kind of hardware, but sort of sort of like 10 qubits, like 15 qubits is like fine, even
Right.
for like messing around with on your laptop. 20, like you kind of need like probably like a little like desktop server or something which is like very deep, like kind of lots of RAM.
Yeah, so it's kind of the usual story.
Yeah, and then like 50 is kind of challenging anywhere.
Yeah, and then 40 you have to pay the original data centers or something.
Yeah,
like that.
and then like 50 is kind of like too far, frankly. So yeah. All right, just wanted to see a list
I
of
just
it.
running, so looking through the documentation here, and I see some of the, there's like flow case states and things like that. I know there's been some work in kind of these many body collective flow case states. I was wondering if it's been used to simulate anything like that.
So or maybe we just want to do a
Many body simulations.
Yeah.
Can you do that with this?
So
But like in a dynamic sense, I guess is what you're talking about.
yeah, so there is actually a flow case solver built into QuTiP, which we won't look at today, but you can do kind of both dynamics. So yeah, and under QuTiP has this range of different solvers for different cases. So we're going to look at SE-solve, which is the Schrödinger equation solver. There's NC-solve, so NE-solve, which is the master equation solver. There's a Monte Carlo solver, and I guess those are the three sort of like general sort of workhorses. Then there's a block Redfield solver for.
But there was no sheet.
I know.
Ah.
Oh, wait, wait, yeah, that's true.
Yeah.
So I would have something like coupled to like one like put on those. There's a flow case solver for like periodically driven like time dependent systems. There's a Krylov solver which can like solve things faster by using this Krylov subspace approximation. There's one called PIX, which tries to take into account the symmetries of the Hamiltonian and kind of avoid like doing like reduce the space by taking into account the symmetries of Hamiltonian, which works well if you have such symmetries and doesn't if you don't. Then there's I guess the one that like I personally spent the most time on recently, which is the hierarchical equations of motion solver, which is falls into like category 3 of the kind of Gaussian approximation.
Right.
The kind of field is I guess used for like kind of fairly cutting edge work where you have these complex interactions with the environment that you want to find.
Right.
So like one of the things that you can sort of simulate with the field is a thing called dynamical decoupling. So you have a qubit which is like interacting, like losing information from the environment, and then but it's the kind, but you know that the kind of interaction is important, and you know that if you like do something like just flip it from like state 0 to 1, then the interaction starts going the other way, and so then what you can do is you can let it go for like a few nanoseconds one way, flip it, have it come back for the same number of nanoseconds, and as long as you keep kind of flipping it backwards and forwards, you can prevent it from coupling to the environment. That's what's called dynamical decoupling. Yeah.
What kind of system is that done on? Is that like a desktop or do you use HPC for that?
Oh, I mean, just the dynamical decoupling simulation. I just run it on my laptop.
Oh.
I mean, that's the simplest version. If you wanted to do something more complex for like a real piece of hardware. Oh, maybe I should show people. If you haven't been there before, there's this page of like QuTiP example notebooks, which range from like how to use Python and NumPy to like like how to do. There's actually, I mean, QuTiP also sort of has built into it like a pulse level kind of circuit simulation. So you could take what we're doing today and then turn that into like into like a implementation inside QuTiP, which would allow you to take like QuTiP's sort of circuit description and execute it on like your model of the device. So there's anyway, if you are looking for kind of examples of what kind of people have done, like this is the page to start. So qtip.org/tutorials. So if you go to QuTiP, you can just look under documentation tutorials and you'll find yourself here. Okay, so what I wanted to do was, okay, I think I wanted to cheat a bit and actually, oops, well, yeah, maybe I can edit this. Just gonna try. Okay, let's just start again. Yeah, I find the. Okay, I'm not sure. So this is just a visualization function, which I wrote for myself like a few days ago. It's actually something I want to contribute back to QuTiP on the visualization side, and it does. Well, maybe you can kind of copy it into your notebooks for now, since it's not part of the main thread of what we're doing. But you can see now if we plot like the states B0P, maybe just do this. You can see the first state is in state 0 and the second state is in state plus. Oh, here I've just rotated the block sphere slightly inside the function just because it was more convenient like angle to look at things from when there were lots of states in this particular case. But so what that does is, so it just creates a normal block sphere with some nice coloring. And it just, if you pass in a list of states, then it just goes to the list and it adds them each to the block sphere, and it gives them all. So qubit 0 gets the first color, qubit 1 gets the second color. And so that's the computational basis states block sphere kind of plotting. That's all just standard stuff we've done. This, like, basically a 3 to the n system to 2 level system. So that's the thing which takes this kind of some like 3 to the n or 2 to the n, well, some 3 to the n system, and basically extracts just 1 qubit part of it to plot on the block sphere. So we can take the partial trace like we did before. So that bit we've done, and that gives us rho. The last bit is slightly dark magic, which I had to kind of do by hand. So that is the thing which converts back from the density matrix to an ordinary kit. And it didn't exist, so I just had to do it by hand. And as you can see here, there's actual, like, literally, like, I'm literally taking, like, I'm literally solving for for what is the state psi such that this is equal to my density matrix rho. So this is the, remember, so the density matrix of a pure state is this outer product of the two states. So and so it just finds out what psi is by literally plugging in like alpha plus I beta and kind of alpha minus I beta and multiply everything out and solving for it based on the 4 entries in the kind of in the density matrix. Anyway, but we don't have to worry about that too much for now. If you're happy to use it, then you can also make kind of little plots like these. Cool. Are people happy with the kind of implementation of the states function? So maybe I can just cut that and plonk it into mine. Yeah. Awesome. Okay, so let's start with like another simple thing that we can do right now. I always remember this interview with Linus Torvalds where they asked him like what his process for like coding was, and he was like, well, I never like use pen or paper, I never write on the whiteboard, like I only type stuff into my computer. And he said, but my process is that what I do is I select the thing that I understand best and do that next. And then I hope that once I've coded that, I understand everything a little bit better, and then I understand something else well enough to start coding. So we know how to make our three like basis states. So let's just call them like, just because we're going to need them a lot. So it's going to, I'm just calling them A and B rather than 1 and 0, just so that I can make them have shorter names. And then I'm going to call this other state R, which is going to be the kind of that very high level state that we're going to use for two interactions. Okay, cool. And then we can also maybe simplify this here by just doing like subscript A. That, I don't know if I need to really do these, but I think I can. Okay, cool. And then maybe let's move that one up so that it's, just hide this away. And then let's do, here we'll do, yeah, just like circuit equals and I'm just going to fill in some atoms. And then here let's do this. Check that everything still works. Okay, great. Okay, so let's start by actually just thinking more about the problem. So we're going to implement these gates by kind of firing laser pulses at individual atoms. So we're going to have kind of some laser pulse, and it will have some characteristics which we'll define in a bit. And it will start at some time, say t0, and we'll go to some time t1, and so the pulse will kind of be pointed at the system for kind of some amount of time dt. So we know that our circuit is going to essentially consist of a list of laser pulses that are going to be fired. So we can do like self.pulses equals just kind of an empty list. And then we're going to, just for convenience, not wanting to like keep track of exactly what time every pulse needs to start, so we'll just send the pulses in one after each other. So we'll just keep track of basically the last time, the time when the last pulse ended. So that we'll just call t the time of when the last pulse ended, and initially it'll be 0. Okay, so great. Okay. Okay, we also maybe should look at our block sphere again. Okay, so what we need to somehow fire a pulse which is going to, if we want to do rotation around the x-axis, which is going to kind of rotate things around the x-axis. So in order to do this, we are going to need to define a pulse, and here we're going to need a little bit of this one. Okay, we're going to need a little bit of this kind of the Schrödinger equation to understand how we're going to do this. So I'm going to think about the Schrödinger equation a little bit like in terms of QuTiP. So yeah, it's this one. I never lost track of which ones are big and which ones are not yet. Okay, so the Schrödinger equation is kind of written down in terms of the wave function, but the exact same equation is going to work for our kind of discretized states. So it says the time derivative of our state psi is equal to minus 1 over h bar times this operator h, which is called the Hamiltonian, which basically just describes how your system evolves in time, operating on the state psi. So in QuTiP, we usually work with it's kind of up to you whether you see QuTiP as always setting h bar to 1, or whether you see QuTiP as expecting your Hamiltonian to already have been divided by h bar. It's kind of up to you when you're working with the system which way you look at it. But in either case, internally QuTiP will just have minus I times the h that you give it as the kind of evolution operator. Maybe we should just go ahead and see like how to solve this in QuTiP. So, I may want to mention just one thing. In QuTiP, you can also supply a time-dependent Hamiltonian, and we'll see how to do that in a second. Cool. So, okay. So first of all, we have to define kind of a Hamiltonian, and the matrix which performs a rotation around the x-axis. So it's in fact a matrix that will rotate the state 0 into state 1 is the operator it's what's called the generator of the transformation or of all the rotations around the x-axis. So what that means is that so it's this operation called Sx, and you can actually just print it out in QuTiP, which I can recommend. So it's QuTiP.sigma x, and you print it out. It's just this matrix, kind of 0 and 1. So if you think of it in terms of a gate, its action is to take the 0 state to the 1 state and the 1 state to the 0 state. So it just swaps the two basis states around. And you can imagine that what the Hamiltonian does is that it applies, if this is your h, so if you set h equal to this, then what it does is instead of applying this whole transformation at once, it applies it like parts of it in little steps over time. So so the time derivative will be kind of a part of that flip. In fact, if you just plug in, if you were to plug in exactly kind of x, then you would get the kind of time derivative of psi is kind of minus I times the swapped state. But then if you instead of plugging in Sx, you plug in some smaller multiple of Sx, you can get it to kind of move slower. So that's what we're doing here in this little cell. So we create this sigma x matrix. We then multiply it by kind of the speed of rotation we want. So we want in one time step will give us kind of sort of all of g. So what I'm saying is going to rotate over sort of a time of 10, and in whatever kind of units we're working in, we're going to rotate pi. And so then I said h equal to g times Sx. So this gives us so g is called the coupling constant and just says how quickly this operation, the swap operation, is applied. And so by making the coupling higher, it's applied more suddenly. Making it lower, it's applied less suddenly. Cool. So the Schrödinger equation gives evolution over time, but we also need an initial state. So I'm just going to pick one. So I'm just going to pick the basis state 2, 0. So just like the 0 state. I'm going to let time run from 0 to 10 seconds just in 20 steps, just so we have something to look at. And then you just call QuTiP.SESolve, where SE stands for Schrödinger equation solver. You give it this evolution operator, the Hamiltonian H, and your initial state. And then you tell it what times. So the t-list does two things. It tells you the start and end time of your evolution, but it also tells you what points in time you want to know the results at. So it's the points in time that you want to know results at, and then the entire evolution starts at the first item in the t-list and ends at the last one. And usually the first item is time 0. Yeah, so the underneath, just to kind of be clear, the solver doesn't hop from one time to another in t-list. The underlying solver will carefully take small enough steps to keep accuracy and such, but it will just kind of only output results at those times. So you can imagine for very large systems, you might not kind of want to have the state too frequently, or if you're evolving for very long amounts of time, you just don't want to try and store everything. Cool, and then we just plot everything on the block sphere again. And so now, what I've done here is that I've just made the earlier states more transparent and the later states less transparent, so you can kind of see what's happening. And so here you can see we start at state 0, and then we rotate kind of slowly, like around, and after 10 seconds we're back where we started. So we've now done a kind of complete rotation around the block sphere, kind of all the way from like the start to the end. So this is kind of exactly the rotation that we want. But we will adjust the amount of time that, or either we'll adjust either the coupling or the sort of the coupling constant. We'll in fact adjust the coupling constant G. But when you're designing these real devices, you might want to keep the coupling low so that you're not putting a lot of like extra power into your system, heating it up and possibly messing with sort of surrounding atoms, and rather have it on for longer. But on the other hand, you also don't want to take too long, because then your system sort of starts slowly becoming noisy and kind of getting kind of entangled with the environment. So we want to kind of do a gate which sort of is very similar to this, except for one thing. As I said, we want to change the time, and well, we want to sort of adjust the coupling constant based on how far we want to turn. But we also have a problem, which is our system is a 3-qubit system rather than a 2-qubit system. So maybe I will, just in the kind of interest of time, just sort of cheat a bit and walk kind of through things. So then we can sort of explain a little bit. Okay, so maybe I just wanted to see if I did an example of I did want to actually, mention 2 other things about SESolve, because we're about to use them. One is that you can apply an argument called EOPS, which gives you, allows you to calculate expectation values of states. Essentially, kind of allows you to sort of produce sort of artificial measurements of the different states rather than storing the full state themselves. Our system is small enough that it's fine, and it's actually nice to work with the full state if you can, because then visualizing stuff is easier. And then lastly, there's an options object, which is an instance of QuTiP.options, which allows you to specify parameters to the underlying like ordinary differential equation integrators. And that's quite important, because especially that there's an n steps parameter, which says how many like micro steps can be taken per kind of big solver step before the integrator complains. So if it's not managing to maintain accuracy and is needing too many steps, it will throw an exception, and then you want to increase n steps usually. And for small systems, it means you just wait like 5 seconds rather than like 1 second or something. But the number of internal steps can get quite large. So I think the default is kind of maybe a bit low. It's like 1,000. But but like 10,000, 50,000, 200,000 like internal steps are very common numbers to work with. And I guess what you need really depends on the entries in your Hamiltonian matrix, like whether there's big ones, and if there's combinations of big ones and small ones, then usually it takes longer because it's trying to sort of maintain accuracy even though there's kind of big changes. Okay. Oh, it also depends what the time dependence of your Hamiltonian is like. Okay, so maybe just want to just kind of maybe go through these little bits.
I guess that solver must be like pretty specialized for these specific differential equations, or?
So it's actually not that specialized. I mean, we have now, and in version, okay, in QuTiP 4, so what we're using now, we really just use mostly like SciPy's like basic solver. You can, and there are kind of various options for using like fancier solvers. So sometimes like we use things from Intel's like MKL library, mostly for performance. What is usually very different is how you actually set up the right-hand side of the equation for you to solve. So QuTiP sets up the right-hand side of the equation for you, which in the case of the Schrodinger equation is really simple, right? It's just like minus I times what you had before. So that's easy. But in other solvers, it gets so. One complication: the Schrodinger equation also, if you can also evolve density matrices rather than initial states, and it all kind of works exactly the same, except that under the hood, QuTiP knows to detect that it's the initial state is a density matrix, and knows to use the density matrix formulation of the Schrodinger equation rather than the state formulation. In QuTiP 5, we've written our own kind of flexible data layer. So in QuTiP 4, underneath the hood, everything is sparse matrices, which is problematic if you have like medium-sized dense states with kind of entries everywhere. And it's also, but in QuTiP 5 we have a pluggable layer, so it uses NumPy arrays for small things, and then sparse matrices when you start tensoring things together. And you can also, there's sort of, I guess, alpha level sort of stuff on running using basically GPU backed memory for this kind of states in the solvers. And we have now our own implementations of, there's these generalized sort of Runge-Kutta class solvers that were developed by this guy Vern, who's got this amazing page. He just classified like all of like the best like solvers and chose like the best parameters. Anyway, so we have our own implementations of Vern 7 and Vern 9, which are different number of coefficients, specifically so we can use our data layer in the backend, so that you can like tell, like in QuTiP 5, you can tell SESolve to, if you pass in a state as sparse, it uses like, it does all of the calculations using sparse matrices, but if you pass in dense, it does all of the calculations using dense matrices. And if you pass in like a GPU backed array, it will use the GPU currently QPy stuff to run everything. I'm not actually quite sure how successful. Like, no one's really used. We're actually looking for someone in a way to use this like GPU backend for like some real things to see how far it can go. We have a Google Summer of Code student at the moment who's doing some benchmarking, and maybe if he does well enough, he'll get to kind of benchmark some of that stuff. So that is the kind of under the hood thing.
Kind of along the lines of, I was going to ask about the GPU thing, so it's interesting that you guys are implementing it. I'm wondering, do you have anything with like sort of like cluster solvers? So you like give it like an MPI communicator, and you have like a big, multi-processor item solver.
So the closest thing we have is we have a TensorFlow data layer backend. So you can use TensorFlow's kind of kind of, I guess, distributed computing like support. But I would really, I mean, one of our sort of projects that we'd like to do, and actually we have capacity from our side, but we kind of need someone who has a real problem and like a real piece of hardware to run on and time to work with us, I guess, because we would like to just add a backend which, I don't know, uses something like Legion or one of the like really big sort of modern kind of like linear algebra on supercomputers packages as a backend and see how far we can push it. But we only kind of, I mean, I guess, so my main task at the moment is getting like the alpha version of QuTiP 5 out the door. And so hopefully that will be done before end of September, let's say. And then we can actually, I guess, start asking people to be like, hey, can you kind of give this a try? Or, kind of what do you think?
Patsy had pretty good pipe last week.
Sorry?
Patsy, the solver suite.
I'm not sure. Okay, so maybe I'd like to, so this pulse that we're going to generate here, so it's going to kind of walk through. So here, I is which qubit we're going to apply it to, and we're going to apply it to the I qubit by, instead of here we just had SX, we'll have, say, if we wanted to do it on qubit 1, we'll have just the identity tensored with X, so this is kind of no change. And then if we wanted on qubit 0, we'll do it the other way around. And if we have like 4 of them, we'll just have lots of copies of I, and we'll have the operator we want stuck somewhere in the middle. Okay, so that's what the I is for. So theta is how far kind of we want to go. And so we're going to, how far you end up turning is essentially the area under, if you plot time, and the sort of amplitude kind of alpha, the coupling strength is the area under this curve. So we're going to just use a square pulse, but in real hardware you would use a like some sort of shaped pulse. Weirdly, the most common pulse people use is the Blackman pulse, which is the same as my wife's surname. And she also did a whole bunch of time series stuff, but she's not that Blackman. But anyway, the Blackman pulses were optimized to cause as little noise on other frequencies as possible. So when you shape the pulse, obviously the Fourier transform now no longer is a single frequency. So okay, so we're going to work out basically, we know that we want the integral to be theta. So we know that we want alpha times t to be theta. So alpha must be theta over t. So, okay, so that's just this here. So this V is the coupling strength. I put like O for omega equals V. So kind of V was the kind of velocity, and then omega is the actual coupling strength to put in, because sometimes for some systems there can be some sort of like other factor involved. But here they're just identical, so I just kind of stuck them in. And then here we want to, okay, I'm just going to make this, let's just call this like place op or something. Okay, and now we have SX here, but let's just first deal with the things that are easy, and then we'll wonder about this. So this is going to, so let's just write like this. So what we're going to do is just do, so we're going to do, so we're going to do, I don't know, ops. We're going to just make a whole bunch of copies of I. So this will be like, QTIP.QI gives the identity matrix on 3 basis elements. And then we're just going to times it by just the number of atoms, so just self.n. And then we'll just fill in, oh, actually I did I first here, I think, so let's do that. and then we'll just tensor them, and then, okay, that's done. And then, okay, how do we actually add the pulse? So def, okay, so here we're just going to have the pulse, which is an operation, and then dt. Okay, so the pulse is going to start at the current time t, and then at the end we're going to do self.t. Well, we're going to just add the end of the pulse to the end. So maybe we can just do kind of end equals self.t plus dt, and then at the end we'll just set this to the end. Okay, so that deals with timing. But now what are we going to add to our, so do we just call this pulses? And we're going to append. Okay, so we want to append our operation. But now that operation, if we just append it like this, will just be applied the whole time. So what we want to do, and here is, in QuTiP you can pass in time-dependent Hamiltonian, and the way they work is you pass in just you make a tuple which just has your operation h and then a coefficient function like f of t, and then the applied thing is just f of t times h. So what we want, since we have a step pulse, is we just want an f of t that is a step function of the time that you want. So we can just do here like f equals okay, so we can just pass it like just make lambda t, and this args parameter, if you need to pass extra function, like extra arguments into your step function, then you can via this args parameter. So then, yeah, so if time is between start and end, then apply the pulse, otherwise multiply it by 1, otherwise multiply it by 0, and now we can just pass in f. Okay, so now we've kind of added our pulses and updated the time. That's great. And now, okay, what is this? What is the self._ab_sx? So what we need to do is we need to now be able to write this matrix Sx, but we want to only write it, we want to now write it for our states AB, which are part of some bigger system. So how do we do that? Sorry? So we do it by noticing that Sx is the swap operation, and we can write that in, so Sx swaps two states. So what that means, if I write this down in terms of instead of 0 and 1, means that A goes to B and B goes to A. Where now A and B are now arbitrary kind of states. So what we want is we want to write this. So we want to take the component of state A and now make it the component of state B. So this says take the component of state A and multiply it by state B. Okay, so good. And then we want to, we also want to take the component of state B to state A, and then apply to state A. So, so this is how we write the swap for kind of any two states. So if it's part of some larger system. So this is kind of what we need to do our swap now as it's kind of unexpected system. So yeah, and I will just, I guess, kind of in order to, now maybe just to like save a bit of time, just do the other ones as well. So I think I just wrote here, just so we have them around for ease of use. Okay, so now we have implemented our first get, and the other ones are going to Y and RZ are going to be very similar. Now we just need to implement run. So going to just so run is actually not too bad. Actually, I'll just take. Yeah, I changed run a bit for convenience. So here, rather than passing in the t list, I just use the fact that we know that the time has to go from 0 to t, which is our last pulse. So we'll use that. And then I just put a number of steps equal to some rate per time, which defaults to 20. And then I added 1 just so that we get like even spacings from 0 to end. If there are pulses, then it constructs. Okay, we can remove this for now. Yep. It constructs the pulses from this QObject Evo. Well, you don't actually have to use QObject Evo, but what QObject Evo does is it takes a list of these like h times f of t, and that represents the Hamiltonian, which is the sum of. So if you have QObj Evo times like a sum of these, or a list of these like tuples, then that's h equals kind of the sum through I of kind of h I times f I of t. So it's just this whole sum. I'm going to give you a time-dependent system. And then, yeah, and then we have our h, and then we just call kind of SC solve in the normal way. I just specified n steps equals 200,000 just to like avoid kind of hassles. And yeah, we pass in the t-list and options, and we return the results. Now, hopefully, actually, maybe I will just actually maybe bring the example that we were trying to run closer up. So maybe we can just uncomment 1. So just do an RX gate, just rotation X. And now let's remove these. Maybe we can just try run our little. This is we have not. Trace up takes 3, but 4 are given. Self trace up. So it's self. We don't actually need to supply n here because maybe we can just chomp these just to save some. Oops. Just to get save some scrolling around. We don't actually don't want any of this. We don't want this last circuit for now. More errors. Op is not defined. What did we do? Because we didn't do. We didn't pass in. We called it pulse, not op. Okay, maybe once more. Okay, so here what I've done is we've started in state 1-1, and so the red represents the first qubit, and the blue represents the second qubit, and you can see that these are the kind of, and we've done a rotation of the first one, so you can see the first qubit. So the second qubit had just stayed where it was because we didn't rotate it, which is good. And then the first qubit has moved from 1 to Y. Maybe let's just look at the evolution. Maybe let's just, no, for now, let's just have a gist at the you can see the first qubit has just moved from 1 and it's moved now to the y-axis because it's been rotated around x by kind of 1/4 of a turn around the Bloch sphere. So that is our X gate. Good. Are people kind of happy with the kind of X gate at the moment? I know we kind of have sped up quite a bit. But the kind of the Y gate is going to be sort of exactly the same. Well, not exactly the same, but very similar. So it's going to, but now we're just going to just rotate about Y. So, yeah, otherwise it's the same. And I guess now let's rotate the second one about the y-axis. Wait, that's the z-axis, right? Cool. And now we can see that now we've rotated it, the first qubit about the x-axis and the second qubit about the y-axis. So looking good. And now, okay, so cool. So Z is also the same, but the control physics underlying all of this are a little bit different, but let's just maybe keep things simple for now. Wait. And now if we can, let's just do one to start off with. Oh, maybe let's do both. And maybe let's try running together. Wait. Maybe let's also change the sign of pi just to make them go in opposite directions, so they're a bit less tangled. Wait. Yeah, so now you can see that kind of each of them, so in opposite directions, undergoes like a rotation about x to y, and then about z to x, and then about y back up to 0. So they kind of yeah, so we can see, I mean, now we have sort of all of the we have all of the basic gates, well, all of the single qubit gates. And I think now what I would like to do is to go through, in our last little bit, just to go through how to do the control Z gate, and then maybe declare done. So maybe we are okay. So maybe now let's go through this procedure in a bit more detail. So you can see here, kind of here our quantum state, and now we're going to use these swap rotations, so the SX that we've been doing, but now instead of them going between the 0 and 1, so the A and B states, it's going to go from we're going to do rotations between between the 0 state and the R state. So if we look at the first one, so that, and we're only going to do ones which do one complete swap. So that's just a kind of 1 pi. So we're going to do on the control qubit for the first one, we're going to try and rotate state 0 up to state R. And if we're in state 1, it's going to fail. So if we just look at the top two drawings, which are when the control qubit is in 0, the control qubit is in 1. If we start with the control qubit in state 1, is going to swap kind of amplitudes of 0 with amplitude of r, but if amplitude of 0 is already 0, that's not going to change anything. And then at the end, we're going to try and swap it back down, just to undo that. And then on the right, when the control is 1, it's going to succeed. So we're going to kind of swap up into state r. And so the first pulse is the pulse 1, and either it will kind of have some effect or not. So if the control is in state 0, it will have some effect. If the control is in state 1, it's not going to have any effect. So kind of here you can see pulse sort of 1 and 3 both have an effect if the control qubit is 1. So, sorry, if the control qubit sort of is in state 0. So if the control qubit is in state 0, we're going to successfully push it into the state R, which is then going to block the interaction, going to block any chance of the target moving into state R because of this interaction, because they're nearby. And the interaction strength will depend on the distance. So, yeah. And then what we'll do is we'll try and, so if you look at the target qubit, we're also going to now try and swap state 0, or move state 0 into state R. But we're now only going to succeed in one case. So we're only going to succeed when the target is in state 0, and the control hasn't been pushed into state R. So the control has been pushed into state R is going to block the target kind of qubit from getting there. So it's just going to be more of these swap gates, but now we're going to fix the angles that we're going through to either pi or 2pi, and we're going to apply it to states of the control qubit or states of the target. So we're going to need 3 pulses. So attempt to drive the control up into state R, attempt to drive the target kind of up into state R and back down, which will either succeed or not. And we're going to then attempt to bring the control back from state R into state 0 if it moved. So there are 2 parts to this. So let's maybe cover the let's maybe do this. Okay, so here there's we don't actually need that. We don't need that. Okay, so this VC is just the again the kind of amplitude for each of the pulses on the control qubit. So it's just kind of 1/2 of pi and 1/2 of 2pi, and then we're going to do again place op. Let's do that. And we don't need the ends anymore. Okay, so we're going to make 3 pulses, and these are just like pulse. We've lost that screen, but it's going to be pulse. The first pulse on the control qubit, which is here, which is going to be just a pi pulse trying to drive the 0 state kind of up into R. And then there's going to be a pulse on the target qubit, which attempts to drive it all the way up into kind of the state R and back down, which will kind of do nothing if it can't get to state R. And then lastly, we're going to bring the control qubit back down. Okay, so we need to define these this ARX. Okay, so that's going to be like the swap gates, but between states A and R rather than kind of the states A and B. Let's do it here, I think. Okay, let's just do it here. Okay, so now we're going to check that runs. So we'll just put in a maybe. Might yeah. One of the unfortunate things is slightly. Actually, maybe we can do this with just this one. So okay, we're going to apply a CZ gates, and in order to see the phase flip, what we'd like to do is to so remember the phase. So the phase flip is just going to put a kind of minus sign in front of beta. So you need a state that won't be visible in a single state if you only had state 0 or state 1. Adding a minus sign to beta would at most introduce like a global phase, so you wouldn't be able to see it on the box here. But if you have 0 plus 1, then putting a minus sign in here switches it to the minus state. So we're going to use a plus state and kind of hope to see it getting flipped. And okay, so let's see if we broke anything. So okay, now we'll probably need the second block sphere. So okay, so here you can see kind of initial states. The blue qubit was in X, and the other qubit was in Y. But now maybe let's see if we can see this here. But when it's 0, it's still got flipped. And the reason for that is we haven't actually, if we go back to here, we haven't actually put in this change in the energy into our Hamiltonian anywhere. So what's happening at the moment is that there is no kind of gap here that prevents the interaction from happening. So we now have to describe in our Hamiltonian what that gap is. And so we should do that. Maybe it's actually easiest to show one of these has maybe it's in here. Okay, maybe I will let's find it in the paper what it has to look like. So there's maybe I think it's up here in the description of the system. So okay, so here is the Hamiltonian. So what we've done here, you can see is the big sum over I. We've added in those HIs of all of our driving terms that we've added into our Q of Evo. So we've done all of those, but this is the interaction term. The interaction term is just kind of a sum between all pairs, and then you only can count each pair once. So that's why there's the kind of I and J, and then the atom doesn't interact with itself. So that's the I kind of like greater than J. And then this number in front, this C6 is just a coefficient that we calculate from the physics of the system. And then the Rij to the power 6 is the curve that I showed kind of like nearer to the start, which is like the 1 over R to the 6 coefficient. And so I haven't included the distance yet. I just sort of assumed that the atoms are like distance 1 from each other. And then this Ni and Nj is just the projector onto the state R. So basically, how much of what is the coefficient of the state R? So and so Ni is just the projection onto the state R for the ith atom. So it's like R times R dot dag. You can just see it up there. So we can add that to our Hamiltonian. So I need to just do this. So just in our we're going to make this H, which I'm just calling H Rydberg because it's for the River Blockade. What is a little bit frustrating and something we should really add to QObj is just something which allows you to construct basically the zero matrix easily. So here I'm just constructing the zero matrix with the dimensions that I want. So if you pass a QObj just dimensions, it gives you the zero matrix. And that's just so that we can have something to add all of these different contributions to. Then self-difference place. So now I'm just going to icon op. We don't need this. So what we're just doing here is just making all of the interaction operators we need. So this is kind of a list of RRI. We actually don't need that anymore. And we'll need to define just this RR. So that's just make 100% sure that I've gotten those. Yep. Cool. Okay, so this here is just creating the zero matrix. This is just creating the list of operators we're going to use. And then we just do exactly the sum that they do in the paper. And we just add I made the coupling one, but it's just, I made the coupling, the coupling must be quite high so that the energy gap is big enough. And then maybe this will even work. I'm going to have a look. I do actually need this. I thought I wasn't using this anyway, but actually I just made. We have created this H Rydberg, but we haven't actually added it into our into here yet. Maybe this is better. Yay! Okay, so that didn't flip it, and maybe that one did. Yay! Okay, and so now we have kind of everything we need. We are like 2 minutes away. I'm happy to stay for a little bit longer if people want to look at things, but I'm also happy to kind of call it here. It has been like 4 hours, which is, I think a little bit brutal on everyone. Would actually much rather have like a whole day or something, so there could be a bit more break. But anyway, yes, hopefully that worked, and I will put the notes and everything in the channel as soon as I've kind of cleaned them up. But we did go through this last bit in kind of a whirlwind. Maybe one thing that I left out that I will just like to show, because I think it's, I mostly kind of left it out a bit because I was hurrying too much. But the actual laser pulses, when you kind of get that like G times sigma X, comes from the actual physics of the problem. So here, like the drive around the kind of here is actually where you work out the effect of applying a pulse, and you get out the sigma X, sigma Y, sigma Z, and it kind of gives you, because we've picked rotation around X or Y, we either have cos equals 1 or sine equals 1. And so these are just kind of this amplitude phi of t. As I mentioned, the physics in the Z case is slightly different. What creates physically the rotation around the Z axis, it's also just a function of t, but it's what's called the detuning. So normally you just sort of send it at exactly the difference in frequency between the frequency of the photon that exactly matches the energy difference. But if you want the rotation around Z, you give a pulse whose frequency is slightly away from that kind of resonant frequency. So anyway, you get a slightly different thing. Cool. Okay. Sorry, that was.
So,
yeah.
My last question.
Yes.
So, you have all of these gates that basically perform rotations on a basis state, right?
Mm-hmm.
If you were to equate that to the classical, bit, all of those are valid states for the qubit to be in.
Mm-hmm.
And infinite now, depending on what phase you give it?
Yes, I mean, it's literally, they cover the entire,
Yeah.
entire sphere. So yeah, there's a two-dimensional infinite space which has the topology of a sphere.
Yeah.
Yeah, yes.
And you're limited only by your computational precision, or like what do you like, or how well you can control the pulses?
Yeah, so there is like a real question here, which is like, can we really access all of those states? I mean, how do we specify like theta, for example? We don't know. Yeah, I mean, we can only, so we have like theta specified as, I don't know, like a 60, like a double precision floating point number. That's still like a very finite number. So the question, there's like a really deep question here, which is maybe only answered, I guess, around maybe like the 80s or something. But the question is, can you essentially, with these gates, make circuits which approximate the kind of infinitely precise circuit well enough? And the answer is kind of yes, you can. So you can show that these that the space of kind of sort of like of states that you can access within your complete system is dense enough that it scales with the basically it remains equally dense no matter how many kind of qubits you have. So you just have to make, so the more accurate you make theta, the more sort of kind of dense you can make it, but there's no parts of this entire space that are sort of not accessible, and there's no sort of evolution, like there's no kind of like real physical things that you can't access approximately. There is a bit of a question whether, so this whole thing falls under the heading of kind of unitary decomposition. So basically, given some evolution of the system, can I approximate it with these simple operations that we have? And so given the answer, yes, you can. But the answer is also, you might need a lot of gates. You might need like a very deep circuit. And I think in general, it scales like 4 to the n or something. So like that's where, like if you have a n qubit system, arbitrary unitaries might take up to 4 to the n gates. And the question is, how much of a problem is that? And there is work which shows that you can approximate them well with fewer gates and stuff. I guess once we get to like 1,000 qubits, we'll start having an idea of how well this works in practice.
But you don't need the whole sphere, right? Like you can do.
Yeah, I mean, to some
You
extent.
can perform computations much like exponentially quicker, even with only accessing like a small proportion of the sphere. Right?
Yes, yeah. So
Yeah.
if you only need to do like, if you only need like 10 gates, then you only need 10 gates to do your problem. So yeah, so there's also a question of like, what are the useful algorithms? Yeah, there's a whole, I guess, sort of land grab, like in a way going on at the moment to try and make useful algorithms, which is kind of fun. I've personally sort of stayed out of it myself. I think my personal feeling is that it looks a lot of fun, but I feel that it's maybe the people who get in on the ground now, I don't know, like make their names, like have their names in lights and become super famous one day for having developed like X algorithm. But it also feels like it's work that will only be used like 20 years plus from now. So yeah, but it is still like a fun game that lots of people are playing.
Yeah.
And if you want money to play this game, also people will pay you to play this game.
Yeah.
Yeah.
Thank you so much.
Thank you very much.
Yeah, and feel free to post questions back or just come find me,
Yeah.
say hello, and
Yeah.
yeah, and I should be around sprints if anyone is still here to like work on stuff. Yeah. Well, thank you very much. And what were your thoughts overall? Like too much? I felt that maybe I knew it was ambitious, but
I think like ambitious to pair code together, not ambitious to demonstrate. So I
Okay,
think
yeah.
that would be the like, if you just do the demo, then I think there would be enough
Oh,
time.
okay.
But because we were at some points trying to also like do it ourselves,
Oh.
I think that yeah.
Yeah. I would
But
really
it
like
was
to just
super
look.
deep, so.
Well, Also, did we spend too much time like early on just like going stuff in detail and then rush too much at the end, or was that the right way to do it?
Well, I don't think you can rush the stuff I mean, at least like for me, I don't think you could have rushed the stuff at the beginning because then you know.
I would not want to try to balance both of those things.
Yeah.
Very audience dependent.
Yeah.
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 Because like if it was just, like, you could skip the whole first hour if we want, you know, like I feel like these guys were responsible for the first hour.
Yeah.
But yeah, so by trying to make it, I guess, well, by making it beginner, I think be sort of like that comes with a lot of setup, I guess, for the audience. So. Which I appreciate, by the way.
Okay.
Yeah.
Yeah. Yeah, anything that you kind of wanted to, I mean, we only touched on like one tiny corner of QuTiP, but if there's anything that people want to know more about, shout or, yeah.
I thought it'd be interesting to have some sort of like environment or noise model. So we're kind of assuming we have a perfect state right now. So it would be interesting to see like, okay, if I have like, okay, 0 Kelvin, right, in some environment, that's how it's going to affect my model. But now it's at, 300 Kelvin, how would that affect coherence time?
Yeah.
Like
I kind of wanted to get there, and it's not that hard. Like we sort of replace like S with M here, and this uses the master equation solver, which is the first like kind of I don't know, maybe this even just, I mean, this should hopefully not, okay, that doesn't change anything because we didn't. So then for the master equation solver, you specify collapse operators. So collapse operators define how the system, master equation solver, it's solving something which is just kind of a bath where kind of all that can happen is you can kind of lose you can have just sort of things kind of, well, the term collapse operator gets described it. You sort of have operations which can kind of cause sort of stuff to kind of like dephase with itself or kind of be lost from the system. So it's just like a very like simple thing that can kind of happen. And so you just specify the operators that you want. And so let's just do place op, I don't know, maybe just on the first qubits. And we want, I don't know, maybe just some phase noise. So that's like AB. So that's just basically this kind of, so the Z operator, if you think of it in terms of like these A and B, just kind of introduces like a sort of phase difference. And then maybe you want to multiply it by something so it's not happening too fast. Yeah, I don't know. Haven't run this yet. Okay, that doesn't really seem to. And then maybe we just need to. Kind of expect. Oh, maybe it's sort of. Maybe it's sort of immune. Oh. Okay. I mean that's. We need to play around with this more and also think about whether that's the right collapse operator for this and whether we can even see it with the control Z. But essentially we're adding these collapse operators which then specify kind of interaction with the system.
So you have to you basically have to derive a collapse operator that you derived off of,
Of the physics, yeah. What you expect the kind of operations to be and then stick them in. And that's, I guess, the simplest sort of like open like quantum thing you can do in QuTiP, and then from there it gets more and more kind of advanced. Typically you use things which structure your bath more and more. So whatever you want, you kind of just describe the bath in more detail and the kind of interactions you get, and you just keep changing which solver you're using and supplying the right options. And then also interpreting the results gets more tricky because then you have this like bath sitting off to the side, and you may also want to, if the bath retains any state, you may want to know what the state of the bath is at some time. So like with the hierarchical equation of motion, you can also get, like you can have currents between the system and like probability between the system and the bath, but you can also, within the bath, you can have like restructuring happening. So yeah, anyway. Like with this dynamic detuning, imagine if you sort of lose stuff to the bath and then somehow get that back out, the bot has to kind of like has to somehow in its internal state keep track of like what's been lost to it. So, yeah, okay. Perfect. Well, hopefully we can definitely look more, and we can maybe even find the popular collapse off phrases for these examples at some point.
No, that was helpful seeing at least how you take it in that direction.